Is that scary a little bit? Okay. So before I go ahead and start, just to know who we have here, could you please raise your hand if you are a master electrician? How many masters do we have? Okay, just to give an idea. Okay. How about journeyman's? Journeyman's, okay. Power limited? Okay, so we have power limited guys and gals. Do we have maintenance electricians? Maintenance electrician too. Okay, elevator people, elevator master and constructor. Is that what you're constructor? Okay. Anybody else that has come in for a different license? How about how many engineers do we have? So I know, do we have engineers, electrical engineers? Not a single electrical engineer? Okay, good. So now I can say whatever I want to say. But before I go ahead and start, guys, I would like to, the second thing I want to ask you is how many of you guys have been in my class before? Raise your hand, so there's a few. Okay, you know, I like to start with LinkedIn, especially for masters, guys. If you're a master or a journeyman or a manager, and you would like to network with all the electrical and non-electrical construction people, having a LinkedIn profile is one of the best things ever created. This is your Facebook, professional Facebook. So I would like to invite you guys to my LinkedIn profile, and I'll go over myself. My name is Chad Kirby. I'm a master electrician in Minnesota, registered electrical engineer. My full-time job is in work for Dunwoody College of Technology. My daily job is in 5 hours. I take 20-some students and I train them how to take a 25,000 square foot industrial building and design a 4,000 amp switchgear service to that building using Revit and CAD. That's the drafting part. Then using the NEC book for all the sizing of the feeders, the branch circuits. We do all the lighting calculation. We do all the power sizing. And then we do, of course, after we finish the project, we do short circuit analysis, arc flash analysis, load flow, all this stuff using softwares. And then when we're done with this, we do specification for the project, CSI specification, cut sheets about all the equipment that we need. And then we use AccuBid and McCormick. How many of you guys use AccuBid or McCormick? These are major softwares that are used by major electrical contractors for estimating. So we teach them how to estimate the project. And then we do presentation to the industry. So that's my full-time job for the last 11 years I've been at Dunwich. Because I'm not busy enough, I carry a master electrician license for a small company called C Electric. I do mostly estimation and help them with the design, especially when it comes to open delta and center cap deltas and all this good stuff. My background is an engineer. I worked for Element Battery, we did hospitals, sport arenas, data centers, wastewater treatment plants with short Elliott Hendrickson. So I did a lot of 600 volt as well as 13.8. So if anybody has some questions about 13.8, 12.47, the higher voltages. So that's my background. As an electrician, I did mostly residential and commercial. Very weak in bending conduits. I'm sure a lot of you guys are bending conduits 10 times better than me. But I did wiring though. I know how to wire for an engineer. Wire really good. So that's a few things about me. Everything that I said is in LinkedIn. Feel free to go there. Because I'm not busy enough, for the last 4 years, I've been recording all my sessions that I do at Dunwoody, including the Revit, the CAD, the CSI specification, short circuit analysis, harmonic, and everything that I do, my training, my 5-hour training a day for the last 4 years is on YouTube. Up to date, we have 450 videos for a total of 1,000 hours. So if you guys have nothing to do and you want to sleep at night, go to one of Chad Curdy's presentations, and the best way to do it, guys, if you hit search here, you can search by topic like ground and bonding, short circuit analysis, arc flash. I did training for 70E. We did it for 3M, Jeff and I for 3M and Mayo Clinic. So if you need 70E training, there are 4 hours free of charge. You don't get credit for it, of course, but on YouTube. So 250 videos for 1,000 hours or more. I love it because I get feedback from all over the country, good, bad, and ugly. They correct me, which is good. I become better, and I hope in the process I contribute to teaching a few people or sharing my information with the others. So that's what I would like to share with you in terms of YouTube. And just go Chad Curdy. You can see the spelling, and you should be able to get into my YouTube channel. 4 years old. If you are a master electrician, must know this site. This is collar hammer. I know some of you guys who are D, Siemens, GE, or collar hammer. If you're in the electrical industry, sizing and specifying, you use one of these 4 manufacturers, right? Collar hammers, 4D, Siemens, or GE. What I like about Collar Hammer, and I use him as an engineer a lot, if you guys have a chance to go to the website, they have something called Consulting Application Guide. If you are being consulted in Delta circuit breakers, you have one of these Delta circuit breakers on. Or if you are to install an impedance, we're talking about grounding today. So impedance grounded system, and you are precise a low impedance or high impedance or reactance to ground your power system. Great information and application and pictures and material about any topic that you can imagine in the power industry. So must know if you're a master electrician and involved in the specification of the equipment and researching it and know how it works. Must know if you're an engineer. So it's really great. That's what I use and what a lot of engineers use when it comes to power distribution system. This topic, section number 1, if you're not familiar with, I know how much you guys get involved in. Most of what you do is called radial power system, which is you bring the service right in to a service entrance equipment and you distribute all this power radially through the whole building, right? Through panels with a couple of transformers in between. That's one power system. There is network power system that they use, like utilities use in downtown Minneapolis, where they network the whole power. So you have multiple sources of power. If you deal with hospital, you deal with multiple sources of power. All this information, how does these power system work? Section 01, power distribution system, awesome. Something like 40 pages must read. Some of it might be above some of your heads if you're not involved in the design, but I thought it's really great. So I like always to share this one with you before we go ahead and start. How many of you guys have this one? I always share this because best practices. Have you guys used the electrical calculator? Now I don't work for those guys, but if you are in are you guys involved in specifying sizing how many conductors you can fit in a conduit? Do you do this? If you're involved in how many conductors can fit in a conduit for feeders or branch circuits? If you're involved in voltage drop, do you have a panel or a load that 200 feet away from the main panel, and you really would like to check the voltage drop on it, right? You get into this situation. Do you get involved? We're talking about grounding bonding. Do you get involved in sizing the equipment grounding conductor or the main bonding jumper, system bonding jumper, grounding electrode conductor? Like I said, all these are right in here. Overconduction device for motors. Jeff was talking about motors yesterday. So to sizing the overconduction device for motors, the overload, the magnetic starters. Unreal. I mean, to use this professionally, guys, you must spend 4 hours on it or don't even buy it. Spend 4 hours. They put YouTube channel on YouTube. There's tons of information how to use it, and I did on my YouTube. I put like 4 or 5 videos how to use it professionally. Great tool. What I like about it, it makes you fast. If you're in the field, instead of grabbing the NEC book and see what type of conduit size, conduit EMT or rigid you need for these 5 conductors, THHN, and 3 conductors, TNW, or 4-aught conductors, 4 conductors, 4-aught, and an equivalent grounding conductor number 2. You want to see, is this conduit really good enough for them? Great tool. Okay, so that's what I'd like to share with you. And before we go, DeWalt, you guys use DeWalt? I always use DeWalt. You have, the ugly, right? Ugly, right? The ugly, that little book. This is 10 times better than ugly. Standard sizes for pull boxes. Standard sizes for disconnects. These are not in any secret book. Standard sizes for panels. All these are right here. 3-way switches, California 3-way switch, if you forgot how to do that. How about a magnetic starter, reversing a 3-phase motor? You just forgot how to do the control circuit and the power circuit for a 3-phase reversing 3-phase motor, right? It's right in here. If you do residential, all the residential code is right in here. All the residential code, as in how many receptacles you need in the kitchen and bathroom and all the habitable places and all stuff. Plus other things. So for $18, must have. Put it in your Christmas list this year. So. So that's what I would like to share with you before we go ahead and start. For grounding and bonding, since you guys are coming here for grounding and bonding, what I have to share with you is this book. If you're an electrician and you need to know more about grounding and bonding, must have. If you're an engineer or a master electrician and you want to understand what is really the difference between low impedance grounded system and high impedance grounded system and reactance grounded system and all this stuff, IEEE has a great book, IEEE 142. That's equivalent to this book for the engineers. So if you deal with engineers and say, well, how do they think and where do they go to get all this information about grounding and bonding, and they seem to be very smart, that's the Bible for the engineering grounding and bonding. Of course, on a practical level, since most of you guys are electricians, this will not specify the wedge for you, the grounding wedge or the bonding bushing. We didn't talk about these. That's methods and material in this book. We have a picture for grounding wedge and grounding lock nuts and grounding bushing. That's why I like this one, and the practical reason this is your baby. Okay, so that's what I have for you guys in terms of grounding and bonding. I do have a couple of things I'll show you later on when we switch to the overconduction device, because we're going to do overconduction device. With it, we're going to talk a little bit about arc flash and arc blast and a couple of other things. So I have a couple of things to share with you. Any comments before we go ahead and start? I tend to have two speeds, like Jeff Kaldick say, fast and faster. So please stop me at any time. There are two types of equipment in the electrical industry, one that runs at 600 volt and one that runs at 400 volt. One that runs at 60 hertz and one that runs at 400 hertz. Because remember that equipment that runs at 400 hertz? I'm a 400 hertz machine. So in terms of speed. Grounding and bonding bugged me a lot. Being an engineer and being an electrician too, it always bugged me, guys. So what I did, to summarize the whole book, the source book, what I thought, or most of it, not all of it, to summarize probably 12 chapters in this book, I thought I got to put it in one sheet that put all these 12 books together for people who are above average in knowing, or at least average in knowing grounding and bonding. So if you've never heard about grounding and bonding, this is Greek to you. But I assume you guys are journalism masters, you passed your German master or power limited technician license or construction license, so they tell you a few things about grounding and bonding, right? So if you're average or above average, this probably should summarize literally 12 chapters in this book. And at MEA, guys, as well as at MEA, we teach grounding and bonding in 8 hours, and other entities, they teach this book in 16 hours. So today, I want to remind you, we're summarizing the whole thing in how many hours? 4 hours. So I thought to summarize the whole thing in 4 hours, this sheet comes really, really handy. So that's what I want to go over today with you in a second. I want to show you the book that we're referencing, one of the best hands-on practical material methods and material grounding and bonding that I ever see. I'm sure a lot of you guys probably recognize that book. So that's what's nice about the source book, hands-on practical show picture type of grounding and bonding for systems and equipment. The sheet that you have in front of you will summarize a few things about grounding and bonding from I'm going to go over them. General, what's grounding and bonding, the difference between grounding and bonding. To ground or not ground, there are, if you guys in the electrical industry, you know that there are 3 types of power systems that we can install in a building or we install for Excel. Doesn't really matter. For distribution, for utility type, or for building type. The 3 systems are solidly grounded system. You take part of the transformer or the generator and you tie it solidly to Mother Earth through some conductive means, aka a ground rod is a good example of that. That's called solidly grounded system. That constitutes 90 to 95% of the power system that you guys dealing with. Grounded system. Literally 90 to 95% of what you guys deal with is called grounded system. So that's system number 1, with advantages and disadvantages. System number 2 is ungrounded system. You heard about ungrounded system. You have it typically as a delta, could be a Y. So your power system is in no shape or form reference to the ground. So I always, for people who don't understand that ungrounded system, imagine a 9-volt battery like this, and you take the positive and negative and put them across a light. A light that rated for 9 volt, the light will go on. That 9-volt battery is not grounded in any way, shape, or form. You take the negative and you tie it to the ground, water pipe or something, now you grounded that 9-volt battery. That's what a grounded system versus non-grounded system is. What you guys deal is like 9-volt batteries, bring it to a light, the light goes on, and a grounded system, you take that negative and you tie it to a water pipe or a rod. Getting a grounded system. That's 95% of what we do in the power industry. The 5 to 10% that we also do is ungrounded system. The batteries is not tied in any way, shape, or form to the ground. That applies for DC as well as AC. So the ungrounded system with its advantages and disadvantages. And the third one is the in-between, a hybrid between grounded and ungrounded. So the smarter than Chad years ago say, well, the grounded system has these advantages and these disadvantages. The ungrounded system has these advantages and these disadvantages. So what if we come up with a system, a cross-reference, or a hybrid between the two systems? That hybrid is called impedance grounded system, which is the best that you can ever have in terms of survivability of your power system on a high voltage as well as in manufacturing and assembly lines and so forth. So these are the, when we talk about grounding electrical system, these are the systems that we're going to go over. Grounding electrical service. When you get into the service, here's my 4,000 amp switch gear or my 100 amp panel in my house. So how do you ground and bond right at the first panel? That's that chapter talk about grounding at the service. Main bonding jumper and at the service, grounding electrode conductor, grounding electrode system and grounding electrode conductors and bonding enclosures. So these I'm going to summarize them, guys, in a couple of sheets. So I always say, to understand grounding and bonding, here's your transformer. Do you want to ground the transformer or not? Yeah, let's ground it. Now you are dealing with a grounded system. Here's your service coming to your building. Grab your conductors from the grounded transformer. Now you're dealing with a grounded system into your service panel, right? Now you're going to ground your transformer. It's already grounded. Now right at the first panel, you need also to ground the system again. When you bring your neutral, what do? You bring a grounding electrode conductor in the first panel, tie it to the steel of the building, to all the grounding electrode system, and tie it to the neutral. So here's your transformer that's grounded. Here's your service that has also the neutral, also grounded the system again at the service. That's what the main bonding jumper is. And then the equipment, the frame, the boxes that housing all the electrical system has to be also grounded. So you create your own grounding electrode system and you ground anything metallic in your building. Anything metallic in your building. So one more time, here's your transformer. Now you decided not to ground your transformer. I don't want to ground it yet. I would run the delta, right? No problem. You grab, here's your delta, ungrounded system. Here's your service panel, main panel. When you bring ungrounded system, there is no neutral, right? So there is no neutral in between them. You're pulling 3 wires for 3 phase. 3 wires for 3 phase, no neutral. The system is ungrounded here. When you come to your service, you have to ground the equipment, not the system. So you still have to have a grounding electrode system. That grounding electrode system only grounds anything metallic in your building. All the switch gear, the switchboards, the panels, the transformers that you want to operate. So the equipment must be grounded regardless if the system is grounded or not. That's what confuses people all the time. There's a difference between grounding the equipment, grounding the system. Regardless of what the system is grounded or not, impedance grounded or not, your equipment must be grounded, meaning reference to the ground. So that's what when we talk about bonding enclosures and equipment. And to ground the equipment, we have the equipment grounding conductor that does this job for us, an enclosure and equipment grounding. So these are a couple of things about most of these chapters, grounding the system versus grounding the equipment and tying the two together. Separated drive system, I'm going to go over these one, guys, with the pictures that I have. So we have a separated drive system. If you own and operate a generator, or you own and operate a transformer, or you own and operate a UPS system, or you own and operate a solar system, you are dealing with something called separated drive system. Separated drive system. I always explain it as you derive a new neutral for the new system. You ground that new neutral, like 28120, and that's what, in plain English, what defines a separated drive system. You own and operate a new transformer. On the secondary side, you create a 28120 neutral, and you ground it. We'll talk about this one in a second. Then there's grounding and bonding at separate building or structures. So you take a feeder from this hotel and take it all the way to a building completely separate from it. How do you do grounding and bonding at a separate building if you're going to a feeder? So these guys, all these summarized, I'm going to summarize them on the sheet that you have in front of you. So the sheet that you have, that I'm going to walk you through it, is summarizing all these, some 12, 13 chapters. Any comments, guys, any questions? So if it feels a little bit complicated, it is complicated. Not really complicated, but it's involved. I call it involved. Comments, questions, how's the speed? Too fast, too slow? Do they keep you awake? Do they give you headache? No headaches? Okay. Let's then I'm gonna switch you guys to the sheet. With this sheet, I have it right in here. I hope I'm not in anybody's way. Um, so here's the sheet that you guys have in front of you. I'm gonna start from the beginning here. So let me see if I can. Okay, so this is. So if you start with the sheet, guys, have three things. First of all, when I put the sheet together, I wanted to put all the grounding and bonding in one big sheet, just one page. I don't want to spread it in multiple pages. That's why it's kind of more involved. So right on the sheet that you're looking at a system that's grounded system. You're looking at a switch. Here's my transformer. That's a grounded, solidly grounded transformer. You can see here. I'm bringing the three-phase. I took the worst scenario, which is a 4,000 amp, 480, 277 system. That's as worst as you can get. Now, go change this 4,000 amp into 100 amp, 120, 240, and you're dealing with your house. Really, nothing will change. So being big amps doesn't mean anything. All the stuff will apply for big amps or smaller amps, big voltages or smaller voltages, as long as you're 600 volt or less. So here's my transformer grounded. Then I brought the power through a meter or a CT cabinet into my first panel. And that's what I'm going to do, grounding and bonding at the service. That's what we call the service. And then I took, from the service, I took multiple feeders. And right underneath it, I feed a transformer that feed a 28120 panel. Can you guys see that? That will give you a separated drive system. Every single respected building that has a 480, 277 building will have these scenarios in it, right? So I have a transformer that feed a 28120 panel. It happens to be 225, commonly used. So that's feeder 1 coming out of the service. Feeder 2 is 1,000 amp. For all practical reasons, that could be your 60 amp going to your this one going to your detached garage in the same building. Could be a 60 amp, so don't let the 1,000 amp scare you. This is the same building, still a 48277. Then a third feeder is going to a separate building. Why separate building? Because that capture grounding and bonding at a separate building. That's a whole it has its own requirement. So a third building, so 3 feeders. And I picked these 3 feeders because these are the 3 scenarios that you're going to encounter. I would say 95% of the time you are encountering these 3 scenarios, right? Is there any other scenarios unless you guys deal with higher voltages? These are the scenarios you're going to be doing. Now to spice it up, you can't have a system without a generator, right? So I threw a 1250 kW generator right next to your hospital or sport arena or your house. And that 1250 kW 48277, we need to do grounding and bonding, and this generator tie it to the switch here. Okay? I hope, I know some of you guys are journalists, I hope that the larger amps or the larger kW and the larger voltage does not scare some of you, especially the green ones. Really, just scale this down to a lower voltages, nothing will change. The only thing that will change is the sizes. The size of the conductors. That's the only thing that changes. That apply to 48277, 28120, as well as 24120 single phase and 3 phase. So nothing really changes. And 50 kW generator, you ground and bundle exactly like a 1250 kW generator. Smaller generators, portable ones have their own rules. Portable ones. Any comments, guys, about what you have in front of you? So that's what we basically have. Now, because of Doubting Thomas, are you Doubting Thomas? Do we have Doubting Thomas here? So people don't say, Chad, you brought this information from your basement. You dreamt of it. So what I did, the second page, and I apologize, the page that you guys have is the second page is front and back. And you might have to go to the back because they're stapled wrong. So if you go to the last page, that's where you are. What I did is I labeled each and every one of these conductors, which I'm going to walk you. Each one of these, can you see 3.1, 6. All these labels, they're labeled for a reason. When they're labeled, then at the second 2 pages, take each one of these labels and identify what is it. It's called grounding conductor. It's also neutral. And where is it? It's at the service. How do we size it? It tells you size it based on the power system unbalanced load, not smaller than main bonding jumper. And if you parallel, don't you dare use less than 1 aught if you parallel. And then, so Doubting Thomas, don't accuse Chad of dreaming of this information. I have all the NEC 2011 references for you, where I pulled this information. Does that make sense? How the whole sheet, and it goes through the whole, the red stuff that you can see, yours is not colored, so it should be kind of a light color here. That red stuff is an example that I took for you. And you can go all the way 1.1, all the way down to the second page, all the way to 7.0, which is equipment bonding jumper. Any comments, guys? Any questions about what you have in these two sheets, summarizing the whole two together? Does it make sense, what we're trying to achieve? Now let's dig a little bit deeper, and if you don't mind, you just sit here. I'm going to walk you, and I wish I could be in a different situation. So let's go and start from the beginning for grounding and bonding. So here's your transformer. Remember we said there is a decision that you have to make when you have a transformer. Are you running a grounded system, impedance grounded system, or solidly grounded system? Grounded system, solidly impedance, or ungrounded system? Very clear. There is no impedance here, and I'm tying the neutral. Can you see the neutral at the transformer, and which is part of the winding, and I'm tying it to Mother Earth. So I'm running a grounded system. By the way, if this was an ungrounded system, everything that you see in this sheet stays identical. The only thing that's different is you see that number 1, which is the neutral, the gray neutral coming in, that will disappear, right? That your neutral will disappear. The only thing, and of course with the neutral comes the main bonding jumper that tie the neutral to the ground. This will disappear. Your neutral will disappear in an ungrounded system. Everything else stays the same if your system is ungrounded. If your system is impedance grounded, the same thing. You don't have a neutral for impedance grounded. We don't pull a neutral. So the neutral will disappear if your system is impedance grounded or ungrounded. Everything else stays the same. Okay, so you're bringing, this transformer happened to be primary 13,800 volt. Don't let this scare you. That's utility owned and operated in this side. On this side, the secondary side of your transformer, 48277, that's my transformer. Now, the utility will operate and ground the transformer when you have a grounded system. So you come down, then you bring a conduit from the transformer into the meter socket. This could be your meter socket, could be your CT cabinet. If it's a small system, your meter socket, right? If it's a bigger system, we call them CT cabinet, 400 amp or higher, we start putting a CT cabinet. So you put your conduits here, the utilities pull your conductors, or the utilities, depending what you do. This is owned and operated by the utility up to the CT cabinet. You pulled your conductors, 3 conductors, they are color-coded per industry, right, for 48277, and the green neutral coming in. So you're pulling a neutral in. And then right here, this is called demarcation point, or the service point. The low voltage known as demarcation point. And the high voltage, we call it the service point. That's your service point right in here. Then you come as a contractor, you put your conduits and you pull your conductors, as many as the engineers or you have decided, and you pull your 4-wire, they call them 4-wire solid grounded system. Can you guys see that? 4-wire solid grounding system coming right in here. So the first thing when it comes to grounding and bonding is you need to pull a neutral, right? Solid grounding. So what do you need to do? You need to size the neutral that you're pulling. You need to size that neutral that you're pulling. So I'm going to take you guys down a little bit to go size that number 1. Cool? The first thing you're going to start with sizing is number 1. So if you guys go to here, here's number 1. It's called grounding conductor. Do we size it based on, here's all the references, based on the unbalanced load, if you know it. If you don't know it, not smaller than the main bonding jumper, that's a code. And if you're paralleling, like a 4,000 amp switchgear, you must parallel. No matter what you do, your conductor cannot be less than 4 aught when you parallel, right? You can't parallel less than 4 aught unless you're a power limited guy or gal, then you can parallel less than 4 aught. You can parallel number 12 if you want to. Okay, so here's what we do, guys. So to size the neutral, first I have to size the service conductors. For those of you who dealt with these, I can carry, for 10 sets of 600 kcm, I can carry a 4,000 amp switchgear. Okay, how do I know that? You go to 310.16.50b16, and it will tell you some sizing. Use the calculator. So that 600 kcm, these are 310 sets. Imagine 10 conduits, 3 phases in each, as well as a neutral, coming to your 4,000 amp switchgear. If it was your building, guys, a 100 amp panel, it will be one conduit with a 100 amp rated conductor coming into it. To size the neutral, it can't be less than the main bonding jumper. So what you do is you take the 10, that's from the code, you multiply it because 10 sets multiplied by the largest size of each set, 600. Then you take 12.5%. I hope you guys are familiar with these numbers. You take the 12.5%, will give you 750 kcm. So then you go to from 750 kcm, you go to chapter 9, table 8, will give you 750 kcm. That's your main bonding jumper. That's your main bonding jumper. That's your main bonding jumper. Then you take that number, guys, and you divide it by 10. Why did I divide it by 10? Because there's 10 grounded conductor in each conduit. Give you 750 kcm. Well, 750 translate to number 1. And I'm paralleling. Can I pull number 1 if I'm paralleling? No. So what do you need to do? The minimum. Why not? That's where the 1 knot came to be. So with the system, I say minimum. You guys can find a lot of engineers, they go pull 400 neutral, and they do these presentations for engineering firms as well. And I'm an engineer. We oversize a lot of stuff. It's kind of cover your butt type design. So, but based on NEC code, all what you need is 1 knot. By the time you reach the 4,000 amp switchgear, guys, everything is balanced. That's carrying the unbalanced load. Not a whole lot. When you reach up to a 4,000 amp switchgear, everything is balanced. So you have 10 conductors, 1 knot each, 1 in every conduit. That's your neutral that's bringing the power to the building, minimum. If you decide to go put 4 knot, bring it on, right? For 250, bring it on. So that's your minimum. Any comments, guys, about these? Any comments about that? So now we brought the neutral and we sized it. Then if you go back up, now we brought my neutral. The first thing that happened right here on the meter socket, now the switch gear, guys, is right here. Inside the switch gear, you will have a 4,000 amp circuit breaker sitting right here. Anything on this side is called the line side of the service disconnect means. You guys remember that? That from here up, that's a line side of a service disconnect means. The code allows you to use the neutral to ground anything on the line side of the service disconnect means. So my CT cabinet here, my meter socket, what else? CT cabinet, meter socket, termination box, they call it. You probably heard all these terms. I can ground it using the neutral, right? Because that's a metallic box sitting outside. I need to ground it. How are you going to ground it? You can use the neutral that's coming from the utility and use it as an equipment grounding conductor, believe it or not, as an equipment grounding conductor, and ground the CT cabinet. Why? Because you're on the line side of the service disconnect means, so-called. Now what the code allows you to do too, also, they allow you to have a supplemental grounding electrode conductor right here. So if you want to go right next to the CT cabinet or termination box that you want to operate, and you want to drive another ground rod and tie it here, that's okay. You're allowed to do that one too. Not required, allowed, right in here. So this box is grounded through my neutral. Now I brought my EM rigid metal conduit into my building. I decided to use rigid, not PVC, for a reason. You're going to see why I've decided. Into an open bottom switch gear. Now when I reach this point here, this is my service, my 4,000 amp circuit breaker sitting here. I have my neutral bar, I have my ground bar. The first thing you need to do is create a grounding electrode system at the service. You guys, right? So the utilities have created their own grounding electrode system here. You are to reference to the same earth that we and the utilities share, the same ground, right? So I'm supposed to create right at the service a grounding electrode system to ground my service. Exactly like the utilities grounded their system, I am to create a grounding electrode system to ground my service. And when I ground my service, I ground everything else downstream. So you come to the ground bar right here, and you take so-called number 3.0. I call it 3.0 for no reason other than I just want to label it. This conductor here is called grounding electrode conductor. It goes typically, doesn't have to be this way, but on bigger system, they have a ground bar sitting in the electrical room. Yep. And they grab that grounding electrode conductor, you tie it to that ground bar with irreversible means. And then from that ground bar, the reason why they put it outside so you can have access to it, measure, torque, do whatever you do, instead of getting inside the switch gear. Remember, you get into inside the switch gear, you got yourself with 70, NFBS 70E and PPE and all this, that you have to put to go torque your grounding. So if you move it out, you have access to it. So you come over here, so that's grounding electrode conductor here. Now right here, all these things that you're looking at right here, these are grounding electrode systems. We'll talk about these one. The NEC book, guys, require you to have only one grounding electrode system. What is a grounding electrode system? A metallic means of tying to Mother Earth. Some type of an approved metallic means of tying in direct contact with Mother Earth. So if your building is steel, or if your building is concrete building and you have concrete encased electrodes in your building, or if your building is steel with foundations, steel foundations with concrete or without, in direct contact with Mother Earth, any of these two will qualify you, you're good to go, you're done. Here's catch-22 though. So if you have steel or concrete encased electrode or steel, you're done. One of them satisfy the grounding electrode system. Catch-22 says if you have other grounding electrode system in your building, you must bond to them. That's how you end up with steel building. You tie to the steel, you tie to the water, you drive a ground rod, especially in bigger systems. If you're a house, if you're a smaller building, and you're in residential, and you decided that only in residential, it's not concrete building, no concrete encased electrodes, so you have to have typically drive a ground rod. In 2011, you have to supplement it by another ground rod because we don't trust ground rods by themselves. And you also have to tie to the water. That was a change in 2011. So you have to have 2 ground rods and a water if you are doing ground rods and water pipe. So if you have, this would be the approved, guys. You can have a wire. You bury a wire underground. You can have a plate. You can have the concrete. You can have a rod. Any or all. You can have steel. You can have a tank. These are all approved methods in the NEC book of tying your equipment to Mother Earth. What we're trying to do, we're trying to create what they did here. Tying my equipment to Mother Earth. These are called grounding electrode system. Tied together, come to my switch gear. Different approved methods. And the NEC book, guys, goes in details in the approved methods. Any comments about what we're doing here? Ignore these coming here. All these grounding electrode systems. I have 3.0 because we size them differently. So do me a favor, I'm going to go size. So I grounded the system. I grounded my enclosure, my box, through my grounding electrode system. So I'm going to go size 3. Let's go just look at how we size 3. So if you guys go all the way to 3, number 3, that will be the first page. Right here, the bottom of the first page. I know they're flipped. 3.0. This is called grounding electrode conductor. Here's how all the information, how to size it, guys. So long story short, you take the same calculation, 10 sets multiplied by 600. These are the ungrounding conductor, the phases, give you 600 kcm. You take the 6,000 kcm to 250.66, give you 3 aught. So you don't have, and the NEC book says stop right here from table 250.66. You do not need to go higher than 3 aught for the grounding electrode conductor. Any comments, guys, about that one? 3 aught. Why did I multiply by 10? Because I have 10 sets. If you're bringing the feeder to your house, you only want set, one conduit coming to your house. So you multiply that number by what? 1. Right? It will be the same number. If you have 12 sets, you multiply by 12. And then you take it to 250.66, get you 3 aught. That's the one that's going to the bar. Now, if you have the grounding electrode conductor, guys, that's going to the rod, directly going to the rod, right? So remember, there's one coming to the bar and one from the bar going to the rod. That does not need to go larger than number 6. Make it, but if it's solely going to the rod, just one rod, does not need to be more than number 6. The one that's going to the pipe, not more than number 6. These are all from the code. If it's going, excuse me, to a plate, it does not have to be less than number 6. concrete encased electrodes. I get carried away. Concrete encased electrodes, not small number 4. A grounding ring, number 2. Where did I get all this info? Right from here. When I say not smaller, guys, you can go always higher. So all these little grounding electrode conductors that tie into the bar do not need to go larger than these. Any comments, guys, about the grounding electrode? And all these are coming from, I pulled this information here from these articles, and I'll let you guys read it on your own. Any comments? So now we size the grounding electrode conductor for a 4,000 amp switchgear. It could be 100 amp hour. Yes, sir.
I have a scenario. What if they ran the conduit, these parallel sets in PVC?
Nothing will change.
And they bring just one ground over rather than paralleling it.
If they brought one, you mean one grounded conductor?
One grounded conductor.
Yeah.
And
When it comes to ground,
stuck it in one of the conduits.
Good point.
PVC.
Okay, now that has nothing to do with this one. That's number 1, the one that we said. If you paralleling with PVC, the code, when you parallel conductor, guys, the code allows you to, the best way of paralleling is to take the 10 sets, 10 conduits. Each conduit will have phase A, phase B, phase C conductor, and a neutral. That's the best way to do it. The code allows you, though, if you have PVC, and the PVC coming from underground, and there is no rebar into the concrete that holding it together, because you have inductive heat. If you pull all phase A, 10 conductors of phase A, imagine putting them in a conduit. Number 1, you almost can't do that in one conduit. But if you put all the conductors of phase A, 10 of them in one conduit, and all the conductors of phase B in one conduit, and C in one conduit, 10 of them, then the neutral can be alone in one conduit. Then when we size the neutral at the top, you don't have to divide by 10. The size of your neutral will be 750. If you remember how we size at 10 here, way at the top, when we came here, here's the size of my neutral, 750, but I divided it by 10 because I'm parallel. So your size of your neutral will be 750 in one conduit. At a system like this, will be really hard though. Right? It will be hard to pull 10. To do this, you have to pull 10 600 kcm conductors in one conduit. There is no conduit that I know of that can handle that. So that, see what I mean? But that's how you size it. Okay, so that's back to the grounding electrode conductor. Any comments, guys, about the grounding electrode conductor? Now, with all these like roots that we did at the grounding, we grounded our building. We grounded our service. That's my grounding our service. So, if you guys go back, now my service is up a little bit. Is grounded, right? So now the enclosure, the boxes, the switchgear is grounded through these systems. My system is grounded, right? Can you guys see that? Here's my enclosure, here's my system. Both of them has its own grounding electrode system. Now I need to tie the two together. How do you tie them together? Through the main bonding jumper. Through the neutral, can you guys see the neutral? Bringing it here, tying it to the switchgear. You take your neutral and you tie it, so you're tying the grounding electrode system of the utility to the grounding electrode system that you own and operate and create through something called main bonding jumper. Any comments, any questions about number 2, guys? So I have my own grounding electrode system for all my enclosures. The utilities has grounded their system, and I want to tie their ground to my ground. I tie it through the neutral up to here, but inside the switchgear, I have to tie my neutral to the ground that I own and operate and created. That conductor here is called 2.0. It's called main bonding jumper. Any comment about the main bonding jumper? How do you size that main bonding jumper? Why do we do that first? Why do we do that?
That's how you tie into theirs.
By the way, I grew up in Jerusalem, and that 2.0 is violation of the code. Just FYI, the utilities will not allow you to ground the neutral, especially for residential. No way. You don't touch my neutral because you compromise the integrity of a neutral, so you don't bond it together. What so
the only place the utility bonds it then is at their transformer?
Well, that's on the secondary side. the secondary side of a transformer.
Right, that's where they found utility bonds in Jerusalem.
No, here. No, here. Oh yeah, for in Jerusalem, yeah, that it's bonded right in here. So that, I don't want to confuse you. That number 2 is violation of the code in Jerusalem. You don't buy it. You don't bond it. And there's a reason for this, though. We're no dummies here, and there are no dummies. When they give dwellings, what do we give dwelling in the U.S.? We give them split power system, 24120. That's called split power system. Split power system is the worst that you can give to any, the worst that you can give, the safest, but the worst they can give to any wood structure. All our homes in America, most of them are what? Wood. So you bring a 24120 to a wood structure, right? Now what happens if you lose a neutral? Now we're at 24120, you lost the neutral here and you're not bonded. You're running so-called open neutral, right? What happens if you have open neutral? The load will share the voltage based on their impedance. Some of them will take the majority of the load, some of them will take little load, and long story short, you'll burn both equipments. So when you burn an equipment, it's okay to burn a plasma TV, but it's not okay to burn the house in the process. So that's why when you bond the neutral here, if you are to lose the neutral coming to your utility, you still stabilize your voltage to ground system. So that's a major safety feature. Now there, they give you 220 to ground. That's it, 220 to ground. Now what happens if you lose the neutral and you only have 220 to ground? Open circuit. Do you burn anything? Nothing. And in a three-phase system, that's in single phase. In a three-phase system, they come here and measure your impedance. If your impedance is 5 ohms or less, they allow you to tie to the neutral. Or actually less than 5. If it's less than 5, they allow you to tie to neutral. 5 or less, you have to maintain 5 or less. You can't be approved if your impedance here to ground is less than 5. If more than 5, they will keep at you driving ground rods everywhere until you're getting 5 or less. In the US, what do we have? 25 or less. 5 or less for telecommunication companies, they use it. Anyway, so that's why we don't bond the neutral. But we're in the US, so let's go 2.0 and go size the main bonding jumper. So for the main bonding jumper, if you guys go to 2.0, here's I'm going to go down into 2.0. It's called main bonding jumper. When it comes to grounding and bonding, guys, terminology is everything. It's not enough to say bonding jumper. If you say bonding jumper, it's meaningless. Is it main bonding jumper? Is it system bonding jumper? Is it supply side bonding jumper? Or is it equipment bonding jumper on the load side? So there's 4 bonding jumpers. So when you say bonding jumper, is meaningless. The same thing like when you say ground. When you say ground is, I'm sorry, but when you say ground is meaningless. What do you mean by ground? Do you mean the grounding electrode conductor, the equipment grounding conductor? What do you mean? So the terminology that we use in the NEC code book is very, very important to understand. So when they said grounded conductor here, that's the term that they use. When they say main bonding jumper, the word main here is very important because that's what the code calls it. If you don't believe Chad, write in here. So how do you size that baby? You size it based on 250.66 on the service conductor. If you exceed 1100 kcm copper, then you have to take 12.5% of the size, kcm size of the feeders coming to your building. So here's what I did. Ungrounded conductors, I have a 4000 amp switch gear divided by 10, give you 400. Go to 310.15p16, and that will get you 10 sets of 600 kcm. Being an engineer, I put a big question mark here, guys, because when you put 10, this is okay if your feeder is coming overhead. If your feeders are going underground, you have trapped heat. When we do this, if you're going overhead with the feeders, 10 runs overhead, EMP conduit or rigid or PVC, overhead no problem, exposed to the air, cool, good. You put them underground in ducts, then you have to encase them in concrete because of stability and all this good stuff. Then we have a software that's called AmpCalc that will come up with a larger size than this because of the heat interaction between all these cables and the heat trap in Mother Earth. So it gets a little bit complicated, but I came up with this size is okay for overhead, even though we're coming from underground here just for sizing. 10, I have 600 kcm. Then you take the same 10 multiplied by 600, 12.5%, that will give you 750. And 750, chapter 9, table 8, you will verify, do they make a 750 kcm? or do I have to sell an arm and a leg to custom design this cable for me? So that's, yep, that's how you verify that they have 750 kcm. So 750 kcm is your main bonding jumper. If it's a wire type, most likely in a switchgear, guys, it's actually a copper sized by the manufacturer. UL listed copper bar that tie the two together. So you don't even have to worry about that. But if you are to size it, this is how to size it. Any comments, guys? Any questions about that? Comments? Did they put you to sleep yet? It's too early. Okay, so let's go. So now this is, you guys are familiar with the main bonding jumper. Let's go down into, now we bonded the grounding electrode of the utility to the grounding electrode that we own and operate and created. Now we have another thing that's called, that's my bonding jumper. This is the 4.0. When you bring your rigid conduit to the bottom of that switch gear, you're at the surface, so you need to bond the conduits to your enclosure. The conduits that bringing the service, if they are metallic, if they're PVC, don't listen to me. If they're rigid, intermediate, EMT, any metallic wiring methods, conduit methods, you need to bond the conduit to the ground inside your switchgear, right? That bonding has multiple ways you can do that. If you are at your house, that bonding would be a bonding bushing, little tiny bonding bushing that you put right here, and you tie it from here to the ground. Done. If you have a hub, threaded hub, that will act as your bonding enclosure to your switchgear or your box. That's another way. There's another method that they can use lock nuts. Another lock nuts, if you're coming into a hole, you're coming to an open switch gear, so you're not tying anything metal to metal here. The conduits are sitting there inside the bottom of the switch gear. You have no option of having bonding lock nuts, or you have a bonding wedge, they call it. So there's multiple options to do this one. For an open bottom switch gear, the only option that you have is a ground bushing or clamp. So you have you put the grounding bushing here, and you take a wire from here to the ground. How do you size that wire, and what's the name of that wire? Now, the name of that wire, guys, is called supply side bonding jumper. See how the term, it's a bonding jumper. You're tying the conduit to the ground. It's called supply side bonding jumper. There are two ways of doing it. Remember, there are 10 conduits coming in here. You either take one from each conduit to the ground, that's the best way to do it in this case, or you take one big fat one, and you go conduit 1 to 2 to 3 to 4 to 10 and to the ground. That's daisy chaining. Two options you can do it. Daisy chaining them is a good if your system is small, because you end up with a smaller conductor. If your system is big, like 4,000, you might end up with 800 kcm. And how are you going to go from conduit 1 to 2 to 3 with all the lugs and tying them with that? It becomes too big of a wire to work with. Okay, so let's go size 4.0. If you guys, so everybody knows what 4.0, bonding the conduits at the service. I want to remind you that could be also a wedge. It doesn't have to be a wire. You'll see later on, it could be a wedge. So if you guys go to 4, here's my 4. Look what it says. Supply side bonding jumper. It's called SSBJ. That's NFPA, NEC 2011, and even before, actually 2008, they start calling it supply side bonding jumper. That's what the technical name for it. That's its legal name. Like my legal name is Chad Curdy. Her legal name here, the bonding jumper, is SSBJ. Okay, so don't call her anything other than that. So, where does it say that? Here's your reference in the code. How do you size it? Same as main bonding jumper. Exactly like your main bonding jumper. So if I'm using one big wire, and go to conduit 1, 2, 3, 4, 5, 10 to ground, that's the size of this wire. Now that would be dumber than a rock to do that, right? Now if you're using one conductor, if you want to take a home run from each conduit to the ground, right? So 10 conduits, 10 conductors to the ground, then you size it based on a 600 kcm, which would be a smaller conductor, more manageable. Any comments, guys, about Mrs. Supply Side Bonding Jumper? Okay, so that's your supply side. Why do they call it supply side? Because it's on the supply side of the service disconnect means, right? That's your supply side bonding jumper. Exactly like the main bonding jumper in terms of size. So that's 4.0. So now we grounded the conduits to the box. We grounded the box, tied the box to the ground. We tied the neutral to the ground right at the service. Now, ladies and gentlemen, we're done with grounding and bonding at the service. You're done. That's what grounding and bonding at the service panel. Any comments, any questions about grounding and bonding at the service? Grounding and bonding at the service? Did I put you to sleep? Or you guys know all this stuff and then repeating something that you know, you don't know? So that's your grounding and bonding at the service. You guys have another energy? Do you need the, here's what I run my classes. I don't know how Jeff does. Every 1 hour I give you guys 5 minutes to spread. So should we have 5 minutes and we'll hit it? But 5 minutes, please. Didn't have? Everybody's okay with this? Give you a stretch. But please, 5 minutes. Okay, thank you. Recoup here a little bit. Any comments, guys? Any questions? Any comments, any questions? I forgot to tell you guys I collect the NEC code book. If anybody is willing to sell anything that, if you have anything in the 50s or the 40s, contact me. I have a full set up to the 50s. All the NEC code books. So I'm looking for something in the 50s and the 40s and the 30s and the 20s all the way to 1897. If anybody's been around, 1897. Okay, so any comments, guys, about grounding the system, grounding and bonding the system? So it seems we have smokers here. Here you go. So we summarize, we grounded the system, we grounded the equipment, we tied the two together through the main bonding jumper and the neutral. Any comments, guys, any questions? So what I summarize, guys, in this 1 hour is basically 2 chapters, almost 4 chapters in that book. Grounding a system, and grounding at the service, and grounding electrode conductor, and main bonding jumper. These are almost 4 chapters in that book, in the one sheet. Of course, the devil in the details. There's a lot of, they show a lot of equipment that you can use. So, okay, now that we grounded the system, we brought the neutral, we grounded the neutral, we created the grounding electrode system. I'm going to take 3 feeders, 3 very important feeders, different feeders, out of this switch gear and ground them and bond them, right? Why? And you're going to see why I picked up these feeders, because these are the most common and their grounding and bonding is slightly different. The easiest one, guys, is the first one. So imagine taking a 1000 amp feeder from the 4000 amp feeder into another switch board or switch gear. No, don't let the amp scare you. That could be, like I said, 60 amps from a 225 amp panel or 200 amp panel in your house. Really the same thing. The only different thing about this panel is same building. There's a big thing when it's in the same building. The grounding and bonding is different if it's a separate building. Okay, so imagine, so then what I need to do is, now we're focusing on the grounding and bonding. Here's my 1000 amp. I need to pull a conductor right in here. Can you guys see that conductor? It's called 6.0. My 6.0, right, this conductor is called equipment grounding conductor. That's the ground, the typically called ground. 6.0 is equipment grounding conductor. Right next to it is 7.0, and the numbers have nothing to do with the code. They're just randomly picked for identification. The 7.0 is, now when you bring your conduits to the bottom of your switch gear, you need to ground your conduits to the switch gear. There are different options of doing that. If it's coming to an open bottom switch gear, you're popping out of the concrete and the switch gear is sitting right at the top of it, you can't tie metal to metal, can you? There's nothing metal to metal to tie. So the only option that you have right here to ground that conduit is something called bonding bushing. That's option number 1. Works all the time. Option number 2, if you're coming to the bottom of the conduit through a hole in the box, so you can't put metal to metal, then then the conduit connection, the lock nuts, will do the bonding for you. You don't have to worry about that. You don't have to worry about it. This is bonding the equipment, not at the service. Bonding the equipment where? At the downstream, at the sub panels. So that number 7 could be a wire, or could be a lock nut, a wedge. Typically a lock nut if you're going like from a 200 amp panel to with an EMP conduit to let's just say going to a 60 amp panel, and the conduit enter the box through a hole, then the lock nuts will get you the bonding for the conduit. And the same thing, 7.0, guys, you don't have to bond at both ends. You either bond at this side of the conduit or this side, or both, the conduit. You don't have to bond at both ends, but you have to bond it at one side or the other, or both. Most of the time, guys, if you are to bond, the same conductor, 6.0, come over here, bond this conduit here, move in with the bonding bushing, bond this conduit, the same conductor, loop it, bond this conduit, and come to the ground. So you can use one conductor to bond the conduits both ends and go to the panel. Any questions about 6.0 or 7.0? Now, how? Yes, sir.
Can you use that conduit as the equipment?
Yes.
The equipment
Yes.
conductor?
Yes.
Have that wire inside there?
Yes. If you are using, now we're getting into the devil in the details. This is a 48277 system. Bonding for 48277 system, if you don't have eccentric or concentric knockouts, very important, means I always say the hole match the conduit. The hole match the conduit, right? You get rid of all the knockouts, and you hold a 1/2 inch hole with a 1/2 inch conduit with no eccentric or concentric knockouts. Your lock nuts will get you the bonding for EMT or rigid, or EMT rigid, PVC is not, or intermediate on the 487. Now, if you have a hole that's 1/2 inch EMT conduit, say, but this it's highly unlikely with these, into a 48277 coming to, you do the knockouts for 1/2 inch, you still have the eccentric or concentric, then you cannot use the lock nuts. You have to use bonding bushings. So that's where it becomes bonding the equipment depending on the voltage. Now, if your voltage 28120, if your voltage 28120 or 24120, you can. You can. If your voltage is 28120 or 24120, that's why you see it sometimes, because the 28120, 3-phase, and 24120, single phase or 3-phase, it doesn't matter down at the equipment level. The only time they become strict on it, if your system voltage is 48277 because of arcing. Okay, makes sense? So now we're bonding with the conduit. Let's go, guys, to 6.0 and 7, all the way to the bottom. So if you guys go all the way to, okay, equipment grounding conductor, that's how the NEC code book call it, EGC. How do you size it? Here's the, can you guys see the reference, how to size it? Here's my references, 250.122, table 250.122. You size it based on overconduction device. And if feeders are paralleled, one full-size equipment grounding conductor in each conduit. This is very important. If you're paralleling, you have to put full size. You don't cut it by the number of parallel. Full size in each one of them. Okay, so I have, let's go to the 100 amp panel. I have multiple examples here. Here's my 1,000 amp panel. Here's my 1,000 amp panel. You take 1,000 amp to 250.122, which I trust that you guys have seen this table before, right? And I'll get you a 2-aught. Then my conductor has to be a 2-aught. Typically, we do this one, guys, if you're using PVC conduit. If you're using PVC conduit, you must. If you're using EMT conduit, then you have the option of using EMT as a grounding, or rigid, or intermediate, or pulling an equipment grounding. Also, you can pull an equipment grounding conductor inside. Any comments about the 2-aught with the 1,000 amp? Okay, so that's your set.
What's the logic that you have to have a full size equipment
They're trying, well, because when you pull the equipment grounding conductor in every set, if you have a ground fault in any set, they want the conductor, the equipment grounding conductor, to be able to handle the largest ground fault imposed on the system with every set. On the system. Because we're sizing it based on the system. That 1,000. See, we size based on what? The 1,000 amp. not on the conductors inside the pipe. So they want that 2 watt to handle the ground fault that could be generated by a 1000 amp circuit breaker, as high as that could be, in every set. In every set. Okay, so right underneath it, guys, this is the technical term for this baby. It's called equipment bonding jumper, and always lose the load side. Where do you find this baby? Right in here, 250.102D. You go, here's my 1000 amp panel. How do you size it? Can you guys see that? Same as equipment grounding conductor. So it's going to be, the size is going to be 2 watt. So that equipment bonding jumper load side is exactly the same as the equipment grounding conductor. That's why what we do typically, guys, is you bring one of them inside the conduit, tie the conduit to it, the same wire, and go to the ground. So you bond the conduit and you ground the system in the same wire with bonding bushing. If you have PVC, what happened? Would 7.0 exist if you have a PVC? Do you need to bond the PVC? No. If we have a PVC conduits coming, of course, we don't have to bond. If you're coming with 2-inch, 4-inch, 6-inch rigid into a conduit, and there's metal to metal contact between the two of them, then 7 does not exist too. For most of the applications, 7 does not have to exist. In 28120, 24120, single phase and 3-phase, the lock nuts will get you there. And threadless or threaded lock nuts will get you there. The only time it becomes an issue if your voltage system is 48277, then, and you are encountering eccentric or concentric knockouts, then you have a multiple other options. You have to have a ground bushings on it. Or the conduit has to match the hole. Any comments, guys, about 6.0 and 7.0? So that's equipment grounding conductor. Let's go back into the sub panel. That's called sub panel. Do you guys see any bonding to the neutral at the second building, at the second panel? No bonding to the neutral downstream. Violation of the code. Because if you bond, then your equipment grounding conductor becomes a carrying conductor and carrying the unbalanced load in the 3-phase system. That's the idea, right? Go bond it. Would the system work if we bond? I'm a devil advocate here. I do a lot of things that's what I did when I was young. Yeah. I always say, guys, in order for the power system to work, all what you need is a hot on a grounded system. Take a hot conductor, go to your backyard, and drive a rod or something in the ground, some metallic object, and tie the hot to one side of the lamp or bulb. The other side, take the ground, and the light will go bright. So you're using Mother Earth as a neutral, not even as equipment ground, against the code, but it works. So for the system to work, all what you need is a hot conductor, right? And a reference to the ground, which could be the ground. Now for the system to work efficient, the smarter than most of us here decided to pull another conductor, make the system work efficient. That's called a neutral. Then we killed a couple of electricians in the process. We said, now we're going to work not just efficient, safe. So those kids can, and men and women can go back to their families. Then we start pulling the third conductor. That's called the equipment ground conductor. That's how that 3-wire that you use for Bryan circuit came to be. One efficient for the neutral, the other one is safety, right? And the hot is to push the power into it. Okay, any comments, guys, about grounding? Now we grounded the box through the equipment ground conductor and the conduits, if needed. Any comments? Am I the only one who's excited here today? Let's go, the one right underneath there. The only difference between the 1000 amp here and the 2000 amp here, other than the amps, the voltage is still the same. Oh, by the way, with the voltage, if the voltage 241/20 single phase, would that be different? Absolutely not. So don't let the voltage scare you or the amp scare you. Same. Sizes will be different, of course. But in terms of the naming, in terms of the how to size it and what, it's still the same. Now, I told a 2000 amp from building A to feed a separate structure or building called building B. Now, I'm a building B. When you go feed, building B is fed from a feeder, not a service, a feeder. When you go to building B, there's a few rules I have to adhere to. Anybody remember the first rule? When you take a feeder to a separate building, you have to have a disconnect for the building. Do you guys remember that? You have to provide a disconnect for the building, typically a fuse disconnect or a circuit breaker, right as you land the feeder to the second building. So you have your circuit breaker right here. You can't have main lugs only in the second building. Have you ever tried main lugs only panel in the second building? Would they allow you? You have to have, then if it's main lugs only, you have to have a fuse disconnect or circuit breaker ahead of it. So this has to be a main circuit breaker panel or a fuse disconnect as you enter, right? That's a must, second building. Okay, now we're not talking about overconduction, but well, we will be later on. So coming into the second panel, three-phase or single-phase, doesn't matter. I brought my neutral, so I have to size my, I didn't size my neutral, guys. I'll show you how to size a neutral there. But let's talk about the ground. The same thing, guys, 6.0 and 7.0. Same concept. Coming to the second building, you have to bring an equipment grounding conductor, and you have to bond the conduit, if it's metallic, as it enters your switch gear at the second building. Could be the same 6.0 and 7.0 could be easily the same wire. Yes, sir.
Does the separate building ground go to the service equipment panel board's grounding bar, or is it tied in the service equipment panel board?
Good point. You're talking about this.
Yeah, where's that ground go?
Okay, good point. Now remember, these are completely separate buildings. Then at the second building, you are to create a new grounding electrode system right in here. New grounding electrode system right in here, meaning you have to tie to the steel, all the grounding electrode system. If you need at least one here, right? Exactly like a service. You need a concrete encased electrode or steel. But if others exist like water, you have to tie to them. So you have to create a grounding electrode system exactly like at the surface, 3.2 I call it, full line equipment grounding conductor all the way to the panel, one or multiple. You can bring some of these here too, exactly like we do at the surface. Now, do you tie this to the top? Is that what you're saying?
Yeah.
Okay. Now this here to there, this, you don't have to because they are tied through what? The equipment grounding conductor, right? Can you see that number 7 here? Let's go back. You see that 6.0 here? It's taking it from here all the way up and tying it. They are bonded together through the equipment grounding conductor. You don't have to. Does that make sense? They're already bonded through the equipment grounding. Did you encounter inspector saying otherwise, or?
I have a problem with everything.
Okay. When we have now you're going to make me put my engineering hat on. When we have guys, a campus. When you have a campus, a good engineered project campus, you will have a one solid grounding electrode system together. So all these buildings will be in close proximity to each other, and they will engineer them all will be tied together. The grounding electrode system will be tied all together. That's the best way to do it. But do you have to if they're completely separate from each other? You don't have to. Would it be a good idea if you have a campus that you bond, every building would have a grounding electrode system and all the buildings in that campus are bonded together? Absolutely. With 1-aught or 4-aught like we do? Absolutely. Absolutely. So, okay, so that's your grounding and bonding at the second building. Any comments, guys, about these?
You're not bonding your neutral to the ground there.
Nope. Do you see any bonding neutral to the ground? They're completely separate.
Does that still apply on farm sites? Farm sites, when you went to separate buildings, they used to bond that neutral to the ground there and consider it something like a separate service.
Now, yeah, these are feeders. Not on you when you do farming. There's multiple ways: 3-wire or what is it called? 3-wire or 4-wire. If you are taking a feeder, you don't bond. If you're taking service conductors, you bond. So it depends. Where do you put the overconduction device? So you have your isolation device sitting somewhere, right? That's to isolate the whole sites, all the barns, everything else. Your isolating device is sitting, no overconduction device in it. Then you take wires up to the pole and you start shooting them all over. Now you take a 4-wire system, you take a 3-wire system in this case, 2 hots and a neutral, to the barn. That's a new service conductor. You bond the neutral at the barn. You go to the house, you bond the neutral at the house. You're taking service entrance conductor. That's one way of doing it. Now you put your overconduction device right at the isolating device to the side. Now your service disconnect means is right there, and then up there you start going 4-wire conductor, right? 2 hots and a neutral and an equipment grounding conductor. Then you don't bond at the barn, but you still have to do what? at the barn, drive a ground rod, and tie. Does that make sense? The 3-wire and the 4-wire, cubic wire.
So they've changed the way you have to do that on farms versus what they did a number of years ago.
There are 3 wires. Well, it used to be they allow you to bond a neutral at the second building. It used to be. They allow you to bond. That's a change, yes. So then will in a case like this, will save you 1 conductor to save money. Then you don't have to put an equivalent ground conductor here. Your neutral will be bonded here, and still acts as a way for existing building. An exception for existing building where you don't put an equivalent ground conductor. I emphasize the word existing, and the neutral will act as an equivalent grounding conductor and a grounded conductor. Then you bond the neutral to the ground. Only on existing building. Okay, any comments with questions? Any comments, guys, about these? Comments? So that's now we grounded and bonded at the separate building. Straightforward, nothing, no gimmicks. If you have PVC coming in here, no need for this. If you have a cable coming in here, directly buried cable to the second building, no bonding, no number 7.0. I have the neutral, guys, 1.2 and 1.2. I size the neutral for you. This is how this is also called grounding conductor. If you guys go 1.2, I size the neutral 1.2. This is for grounded conductor for the panel, for the 2000 amp panel. This is how I size a neutral. There's the code says, guys, based on the unbalanced load, but you go to a service and you have no idea how much you can. If you're at this level, you have to calculate your load. But if the worst scenario that you're going to encounter is you take, this is a scenario which is coming from 220.61b. That's I use all the time. So you take, assume all this load could be neutral, which is worst scenario, and then apply the 200 amp, higher the 200 amp cut by 70%. Do you guys remember that rule when you size your neutral? And then you end up with 5 sets of 350. Why 5 sets? Because I'm taking 5 sets to feed the sub panel. So that's how we size the neutral for the 1.2. 1.1 right above it, the 100 amp. Here's my, so we have, what was it, 1.2, 2000 amp. What was that number for? Okay, for odd supply side 1 in jumper. Can't remember what. I don't know if 1.2 and 1. Oh, both of them are 1.2. Okay, that's why. 1.2. So that's how I size it for. I size it for one of them. 1.2 for the 2000 amp. For the 1000 amp, the same thing, guys. You take except you put 1000 amp here. So 1000 amp minus 200 multiplied by 0.7, and add in 200, give you this number. How many runs you want to run? You have to know how many runs because you paneled it. I'm running 5. Get you this amp. And that's how you size your neutral. That's worst scenario. The best way to size it is you know what the balance, what's the 3-phase loads. All of your 3-phase loads will not contribute to the neutral, throw them out. Then your lighting, 277 in this case, the only ones that are going to contribute to size your neutral. But remember, no matter what you do here, when you're pedaling, no matter what you do, can you go less than 1 knot anyway when you pedal? So that's how they catch you. If you're pedaling, you can't go, even if you came up with number 6, a ground conductor, can you do that? You have to go 1 knot. Okay, so that's my sizing, my neutral for this system. Any comments, guys, before we move into the separate drive system? So I took 2 feeders, one same building, one separate building. The second one right next to it is another feeder that feed a separate drive system. Before I move there, any comments about the same a sub-panel, so-called sub-panel, in the same building or a separate building? Straightforward, right? Any comments, guys, about that? So now let's take another feeder and feed so-called separated drive system. Now I took a feeder from the same switch here to an owned and operated and installed transformer. I own and operate and install this transformer, not a utility. Typically, and from this transformer, I dump the power into another panel at a different voltage. Only in the US will you see a system like this. I mean, most of the world guys use, I don't know if you know, use 220 to ground, 220, 230, 240, or 250 to ground. So they burn all their lights and receptacles 220, 230, 240, or 250, all Europe. Almost 80% of the world at 220, 230, 240, or 250. Okay, and then with this goes, that's line to neutral or line to ground. With this goes 380, 400, 415, or I can't remember, 430 or something. That's the line to line. So 380 is your line to line. So you burn all your air handling units, all your chillers, all your big equipment, big power equipment, you burn them at 380 or 400 volt, three-phase, line to line, and your lights and receptacle will be burning at 220. So this boy, no exist. Utilities use with transformer, unless you have other systems, unless you buy a system from the US that you know, equipment that you run at 2.8. So they have 1 voltage in most of the building, which just makes it a little bit easier. But we're America, we like to do a lot of big stuff, right? So here's my transformer that I own and operate. Primary is delta. These are separately derived systems. The reason why they call them separately derived systems is I want you to focus on the delta and the Y. Don't look at the green. Just look at the other colors other than green. Is there any physical, mechanical connection between the delta and the Y? So complete separation, right? That's what a definition of a separately derived system. No connection whatsoever between the primary and the secondary. How would you make a connection? Take that neutral here and tie it to this neutral here. Now that's non-separately derived system. Not like you would do that. You wouldn't do that on the 208, 120, 277. These are two different neutral. That my white neutral is 120. My neutral up there is 277 neutral. Okay, so that's what they call a separately derived system. Completely separation between. The only thing that tied between the whole system is what? The grounding and bonding. You still have to ground and bond above, ahead of the separately derived system and after the separately derived system. Okay, so my delta Y typical. I brought my feeders here. The first thing you need to do when you have a separately derived system, as the code says, you have to take a grounding electrode conductor either to the transformer, which you want to operate, or to the panel, typically at the transformer level, and that conductor right here, 3.1, take it all the way to the grounding electrode system inside your building. Tie it to your grounding electrode system inside your building. There are multiple ways of doing this, guys. If you're building a steel building and your service is 500 feet away from where this transformer is located, you can just tie directly to the steel and you're bonded. Another option that we can, if you water pipe in an industrial establishment, Jeff, you and I would do that one. You would take your transformer one end, tie it to the water pipe, that continuous, clear, you can see it. At one end, tie the transformer to it. The other end, the service tied to it, and that will bond the two together. If you don't have these two, you are to pull a grounding electrode conductor from wherever this boy is sitting, all the way to where? To the grounding electrode conductor. Grounding electrode system inside your building. Grounding electrode system inside your building. Okay, so the first thing I want to size, guys, is actually, I want to size, so we size, let's go, now coming to the transformer, you have to bring, can you guys see number 6.0? 6.0, that's an equipment grounding conductor to ground the transformer. You still have to pull an equipment grounding conductor to ground the transformer. And also you still have to bond the conduit, if it's metallic, the metallic conduit to the enclosure of the transformer. Bonding bushing. Again, 6.0 and 7.0, the equipment grounding conductor and the equipment bonding jumper load side can't be the same wire. So you come loop it, bond the conduit, and get into the ground bar inside the transformer. So let's go, guys, size 6.0. So, and I'm bringing on the primary side, you bring 3 wires, because it's delta, and an equipment grounding conductor if it's an EMT conduit, if it's a PVC conduit. So an EMT conduit, typically we have a flex to tie to it, so you have to pull an equipment, tie the jump over the flex from the EMT with a bushing directly to the enclosure. So you have to have mechanical, good, solid mechanical connection between whatever conduit, metallic conduit you have, and the frame of the transformer. That could be a conductor, that could be, if you're tying your rigid or EMT directly to the transformer, which we wouldn't do that unless you're coming from the bottom, then that bushing could do it, but most likely it would be a bonding bushing right in here with your equipment grounding conductor. Okay, so let's go 6.0 for the transformer. If you guys go to 6.0, The same thing for a transformer all the way. This is how we size that baby for a separate drive system. So equipment, let's go to equipment grounding conductor 6.0. That was for the transformer 750 kVA transformer, right? That's my transformer size. You find the full load current of this transformer, assume it's continuous current, so you multiply by 1.25, that's what you get, 12.85. Then you go size the overcome protection device 125. Now the code allows you, I don't want to make a transformer, allows you to go higher than that, but typically guys, if you size your overcome protection device for 125 and go up, and I ran, as an engineer, I ran a lot of coordination curves for these, you will get there, it will get you there. Though you can't go higher than that. So I went to 125 circuit breaker feeding that transformer. From 125, equipment grounding conductor get you number 6. So you have to size the overcome protection device that's feeding that transformer based on the amp size of that transformer and 125 amp. You can go up to 250 though. Conservative here, and then the size of the conductor will be number 6. Now the same transformer, guys, the equipment bonding jumper, it's called what? Same as equipment and conductor set. So equipment bonding jumper, the load side for the transformer is the same, number 6. That's why we use the same wire. Come in, bond the conduit, the flex, and go inside the transformer. So that's for the equipment. That's grounding the transformer. So let's go back. Now that's exactly like any other panel, by the way. Up to this point, we really haven't done anything here. Right? We just grounded the transformer. Now you need to take the equipment grounding conductor. Can you guess 3.1 here? Going all the way, you need to size the grounding electrode conductor. So go to 3.1, will ya? 3.1. Okay, here's my 3.1. I have 3.1. The way we size the 3.1, guys, is based on the size of the feeders coming out of the transformer on the secondary side of a transformer. So it's called grounding electrode conductor at the separate drive system. Remember, I have 225 amp panel tied to this secondary of the transformer. If you go size the conductor for it, it's 4-aught, right? You guys size this many times. 4-aught to feed the 225 amp panel coming out of the secondary transformer. From the 4-aught, you go to 250.66, give you a number 2 grounding electrode conductor. That's the wire that you have to take from the transformer all the way to your grounding electrode system. Any comments, guys? Any questions? Comments, questions? So that's my grounding electrode conductor coming out of the separate drive system transformer. That conductor can be directly tied to the steel of the building, can be tied to the water pipe, or can go all the way back to the ground bar in your building. Any comments, guys? Any questions? Oh, yes, sir.
Let's say you take that bottom up panel board on your drawing and turn that into an isolated ground panel board.
Okay.
And I had this actually happen not too long ago. And I wanted my isolated ground to go all the way to the building entrance grounding bar, my isolated ground conductor, and the AHJ was wanting me to ground it to the transformer, because there was a transformer there. And so, anyway, he let me do it my way, but he was a little concerned about that. I didn't want to ground with it, so I didn't want to tie it to the transformer, because some of the equipment was tied to other equipment not on that panel board via Ethernet cables and so on. So I wanted one grounding point, so I had them take it all the way back to the building entrance grounding bar. Anyway, it worked fine, but
Did you also pull another?
yeah, there's two grounds.
There's 2 grounds. So you did this. In addition to this, you pulled another ground, and you pulled it all the way back to the service. I don't see what, if that stabilize your low voltage system and make it with. The insulated ground is not for the power reasons. We pull insulated ground to make sure that our electronic equipment are safe, right? That's so if your equipment works, I don't see why you can pull it all the way back to the source.
Because he kind of argued with me a little bit. He went tight there, and I thought that developed a ground potential.
Yeah.
He didn't understand this.
I don't see any conflict that happened. They're all bonded at the end, at the panel. You're just providing, well, I can see what his point is, because this is separate derived system, it's like a service. So as a service, I can see why he wants you to bond everything at the service. He's treating it like a service. Everything has to be bonded together. But unless there's anything that I'm not aware of, I don't see why you can't pull it all the way back.
I think you're probably just as well planned to put a ground right there that typically drives them. It goes back to the annex.
The only thing is that some of the equipment that was hooked up to that last panel board was hooked to other panel boards that weren't powered from that separately drive system.
Yeah, they have
And
multiple.
I was afraid I'd get a ground loop between the transformer, the separately drive system, and the ground bar.
Yeah, so you have.
Everything was set, all my IT equipment, everything was set up as separately drive system. Only then I couldn't understand that was okay.
Yeah.
But since it wasn't, I wanted to go.
But I thought, if I remember right, I thought this isolated grounding electrode system is allowed to go all the way to the service.
It's allowed to.
So I don't see it. You can take it all the way to the service, as long as you ground equipment. So
You basically treat that as a drive.
yeah, yeah. But I see his point though. Yeah. But yeah, you can pull it all the way. Okay, so we got that one. Good point. So we grounded the grounding electrode conductor, guys. Now coming out of the secondary side, the first thing you need to do is bond the newly created. This is a newly created and owned and operated neutral. That's not the one the utility gave you, right? You created that neutral, you own it and operate it, right? And maintain it. So here's my newly created neutral. You have to bond the neutral to the ground. So you bond it all the way here to the ground. And we take it all the way to the same reference. Can you guys see that ultimately the neutral of the 277 and the neutral of the 120 are tied together at the surface, right? If you look at follow this, they're all tied together where? At the surface. They are, but they want you just to tie them at the surface. That's all. So here's my newly created neutral. I bond it to the ground. That wire here, which could be also other than a wire, is called 5.0, right? That's my 5.0. That's called system bonding jumper. Exactly like the name bonding jumper. Except the term that they use for it is system bonding jumper. So system bonding jumper. So let's guys go, and as long as this is my system bonding jumper. So let's go size the system bonding jumper to 5. Very quick here to 5. And all the way, if you look at 5, here's my 5. System bonding jumper, that's what they call it. Not separated drive, system bonding jumper at the separated drive. Here's my transformer. You size it, you size your conductors first, and then from your conductors, you size the system bonding jumper number 2. Exactly like the grounding electrode conductor. Except if you go higher than 1100 kcm, if you go higher than 1100 kcm, or God forbid you're using aluminum, you can lose aluminum, 1750, then you start taking 12.5%. It's like exactly sized as the main bonding jumper. System bonding jumper and main bonding jumper are identical in terms of sizing. So that's called the only difference between them is the name and where they're located in the system. So that's my system bonding jumper, and its size is number 2. Any comments, guys? Any questions about the system bonding jumper? System bonding jumper. So we went to my system bonding jumper. That's the first thing you do is you have to ground your neutral. Why do we ground your neutral? When you ground your neutral, you stabilize it, right? We stabilize our newly created ground. We're running a grounded system. That's a system that we grounded. We stabilize it. Solidly grounded. Can you see that? Solidly grounded. So we size my neutral. Then you have to pull a grounded conductor. So let's go size the grounded conductor, 1.1. I typically go, if you guys go to 1.1, that's the neutral coming out of the transformer. So my neutral, it says grounded conductor at the separate drive system. A lot of us engineers, I'm sure you guys agree, if you have anything 300 amps or less, full neutral, especially panels 480, 277, 28, 120. It's not worth derating a neutral on a system 300 amps or less. After 300 amps, you start. Typically 225 amp. Why? Because there's a lot of neutral load in it. These are feeding lights, or in this case, they will be feeding receptacles and lights. A lot of neutral load. So in this case, I pulled full neutral. Can you guys see? my grounded conductor here. I took 225 amp and I sized my 4R and system bonding jumper is 2, so my grounding conductor is 2. Now, the code says, guys, this neutral cannot be smaller than the system bonding jumper too. So I can't pull less than number 2 even if I tried. It has to be at least number 2. But I like to pull full neutral for this system. Any comments, guys, why we pulled smaller amps, 48277, 28120, though it's good for neutral, but I could have done number 2. The minimum is the system bonding jumper. So I size my neutral. Now the second thing that we need to do, so now we bonded the neutral here. We don't bond the neutral again in the panel. You're not allowed to do that. You can either bond it here or here, but not both. So we bonded the neutral here. We don't bond them here. We keep them separated. Then we size the neutral. Then you have to pull that little wire here. It's called 4.1. The conductor coming right through. Bond the conduits from one side at least, or both. Better both. And you bring it here. This 4.1, believe it or not, it's called supply side bonding jumper, not an equipment grounding conductor. Why supply side bonding jumper? Because it's on the supply side of the separately derived system over current protection device. Because you put a circuit breaker, you have to. Can I put, this is main lugs only? You have to put an overcurrent protection device right here, inside the panel, outside the panel. So you are on the line side of it, so that would be supply side. That's called supply side bonding jumper. Exactly like the supply side bonding jumper at the service. Okay, 4.1. How do you size the 4.1? We know it's supply side bonding jumper now. So my supply side 4.1, if you guys go all the way to 4.1, 4.1, it's called supply side bonding jumper, and it's sized exactly as what? SPJ, system bonding jumper, and it's number 2. So I hope that referencing it, you don't have to worry about it. It's exactly like a system bonding jumper all the time. All the time. Whatever your system bonding jumper is, the same size is going to be for the supply side bonding jumper. The only time it's different though, let me tell you one time when it's different. All the time. Now the exception, there's always exceptions. I'm sorry. Always exception. If you parallel, if you have multiple conduits coming into that transformer, then you have 2 options. Either daisy chain all of them, same as the system bonding jumper, or home run from each conduit. Now it becomes slightly different. Home run from each conduit. But still cannot be sized the same way, but with the home runs. So that's the system supply side bonding jumper. Now with your supply side bonding jumper, on the secondary side, you're going to bond the flex that's coming to your building from one side or the other, or both, as you enter. So that conductor, guys, 4.1, could come here, bond the conduits here with a bonding bushing, come inside it. This is a flex, we're using flex. Coming out of here, bond the end, and come all the way back. You only need to bond one side though. Yes, sir.
You said you could bond it in that panel board.
Yes.
You didn't bond it in the transformer.
Yes.
Is there a preference? Does it functionally work better one way or another?
If you own and operate the transformer, it's better to bond as close to the source of power of your separate system as possible. So that's the only thing, as close to the source of power. My source of power here is what? My transformer. So bonding at this one would be the preferred method. Because you own and operate this transformer too. I mean, it's not, that was utility transformer, you can't get into that enclosure. So, and from an OSHA point of view or 70 point of view, what's the difference between getting into here? Well, that might be a little bit, if you put it here or here, from 70E, now you are in both sides on the line side of the disconnect, which means you expose almost to the same amount of arc flash, arc blast. Because you are, when you're in this panel, you are exposed to the line side of the arc that could come from the line side of the disconnect, right? You could arc the line side, not the load side. So from an arc point of view, you're exposed to the same hazard. So, any comments, guys? Any questions about that? Comments? closer to the source. So now we bonded. This scenario, guys, you're going to see over and over in every building. Every building that you encounter, that sub-direct system that we use in the US. So that's another whole chapter that talks about bonding for sub-direct system. A couple of things. If this transformer, how many of you guys, let me ask, that came in 2011. How many of you have a sub-direct transformer other than generators, that's located outdoor, like a transformer? You take a 480 to outdoor, feed a transformer, and come indoor. Not often, unless you want to feed a separate building. So say if you take a 480 from here to a transformer outside that you want to operate, convert it from 480 to 277 to 281, 120, feed another building. If you do it this way, then you are to drive a ground rod right outside next to the transformer because of lighting and so forth. So what adds up here is right here you drive a ground rod right in here for the transformer, and you don't pull that one all the way back. You drive the ground rod right here, and then the whole system is bonded together through the equipment routing conductor. That's if you are outside. That typically for generators, for the generators that we do. We're coming to the gen in a second. Any comments, guys, for sub-direct system? So this is a transformer. It's a in 2011, yeah, 2011. Absolutely. If your transformer is where? If your sub-direct system is located outdoor for lighting and so forth. If it's indoor, you bond to, and why would you put it outdoor? The only thing I can think of putting it outdoor is if you want to feed it a separate building. Or cooling, there you go, good point, yeah, if you want to cool it and bring it back, yeah.
It's in the building, yeah, get exhaust out.
That's generator, what we're talking, like for generators, yeah. But for transformers, but you have to drive a ground rod. We'll get into the generator in a second. Any comments, guys, about this? Now, if you guys do solar photovoltaic system? Nobody? And now, the only thing that's not covered here is bonding for solar for DC system, solar photovoltaic system. You know, the same thing you have to typically, they take the grounded conductor, they ground the negative, they take the grounded and they ground it to a fuse. So you take the negative to one side of the fuse, out of the fuse, tie it to the ground. So negatively grounded solar photovoltaic system, that's how they do it. They size the conductor based on the size of the hot conductors coming to the combination box. So if your positive conductor is 1 watt for that system, your grounding electrode conductor would be 1 watt. It's not here. Any comments, guys? Any questions? Comments? Let me take you to the last one, guys, on the grounding and bonding, which is the generator that I know you guys were waiting to hear the generators, right, for a long time. So now I have separated drive system transformer. That's a load, right? Transformer is a load, even though it's a source of power. But ultimately, the transformer does not generate power. It receives its power from the system, converted to a different amp and voltage level. That's what transformers are, to match the equipment. Generators are completely different. Generators are voltage and power generators. So they can give you power at different voltage or the same voltage like in your system. Typically, if you have a generator, guys, if your system is 480 and your generator is 208, that's a mismatch. You know, then what do? You put the transformer, step it up. But typically, if your system is 480, you have a 480 generator. So my generator is 480. My generator size is 250 kW. It could be a 500 kW. It could be 100 kW, 50 kW, same calculation. Now, when you have generator, you have the option. Since the voltage, can you see the voltage? The neutral voltage is 120, great, same as the neutral voltage here. Then they give you the option, bonding the two neutral together if you want to, or not bonding the two together. In the transformer, we did not have any option, did we? We can't bond the neutral of the two together, right? Except we at the panel. On the generator, you do have an option. So you can run this generator separately derived system by isolating the neutral. Then if you have an auto transfer switch, you have to have a 4-pole auto transfer switch, 3 for the 3-phase and 1 for the neutral, flipping them. or you can run it as non-separated drive system, and then you have to have then a 3-pole auto transfer switch, and you only switching the phase A, B, and C, or hot 1 or hot 2 if you're doing single phase. In either way, the grounding and bonding are the same, except with some exception. So the scenario that I'm having right now here, guys, is, well, there's exception always. The scenario that I have is for separated drive system. Separated drive system. So when we have a separated drive system, this generator is running a separated drive system. So when I switch it, I have to switch what? 4. The 4 I have to switch it. The 3 phases and the neutral. Separated drive system. Now when you run a separated drive system for a generator, the first thing you need to do for the generator is take a grounding conductor and tie it to the grounding electrode system inside your building. If it's outdoor, you can drive a ground rod here, tie it to the ground rod, and it will be bonded to the system through the grounding, this is called supply-side bonding jumper, through the supply-side bonding jumper right in here. So let's go size 3.1 first, or maybe this size a neutral first. I have a neutral coming out of this generator, and I need to size that neutral, right? So let's go to 1.1 first, size that one. So if you guys go to 1.1, okay, for 1.1, it's right in this side for the generator. Generator, to size the neutral, you have to size the phase, right? So generators, you take the 250 kW, divided by 0.8. Anybody knows why 0.8? kW, you have to convert them into kVA. So I converted the kW to kVA, and then I converted it to amps. At this amp level, guys, at this amp level, we're looking at what, 1882 amp. At this amp level, you don't multiply it by anything, because they call them 100% rated circuit breakers. Anybody have heard 100% rated circuit breakers? So the circuit breakers are 100% rated, and they work. They don't have to derate them. So we take this number here to 240.6 and size your overcap protection device, 200 amp and 2000 amp. If that was your 50 kW transformer, all what you have to do is take the amps that you did here, multiply it by 1.25 for continuous load. That's all what you did. At this level, like I said, you go 1000 amp or higher, almost all your circuit breakers are 100% rated circuit breakers. Meaning, if you have 100 amp, well, if you have 1000 amp, you can pull 1000 amp out of 1000 amp circuit breaker. Right now, if you have 100 amp, how much continuously, 3 hours or more, you can pull out of 100 amp? 80%, only 80 amps you're supposed continuously. What happened to the other 20 amps? Those are the non-continuous things, the things that run for 2 hours and 59 seconds, 59 minutes, right? I'm trying to be, so they run fully loaded, 2 hours and 59 minutes, that's non-continuous load, based on NEC code book. Okay, so you know why I did not multiply, so 2000, then from the 2000 divided by 5, I want to pull 5 sets, I sized 5 sets of 3 conductors, 600 kcm. Why 3 phase? Then what I do with the neutral, guys, is then that's the 3 phase. Then I take my neutral, I take the 2000 amp exactly, and I apply this rule 220.61b on it. And the first 200 amp, leave him alone. Anything higher than 200 amp, cut them by 0.7. So that's what we did. We cut it by 0.7, came up with this. Divide by 5 because I'm parallel, and my neutral and the 5 sets of 350 kcm. In no case shall your neutral be smaller than what? The system bonding jumper. In no case. Your neutral can be smaller than the system bonding jumper. Exactly like at the service. In no case shall your neutral or grounded conductor be smaller than the main bonding jumper. So that's the size of my neutral. 5 sets of 350 kW. The KCM. Any comments, guys? Any questions? How many of you guys have sized these? Anybody sized big stuff? Or if it's don't let it scare you. Put 50 kW here and do the same thing. Just multiply by 1.25 here and same sizing. So no gimmicks on that. Okay, so that's my neutral. Why do I size the neutral? Because the neutral, guys, is a grounding conductor. Our topic is what? Grounding and bonding. Neutral is called the grounded conductor. So that's why I'm worrying about the neutral. You need to know how to size it. Okay, so we size our neutral, guys. Then you have to tie your newly created neutral that you own and operate at the same voltage, 277, tie it to the grounding electrode system, bond it together. 5.0, guys, it's called the system bonding jumper, exactly like at the transformer, system bonding jumper. So let's go to 5.0 and get my system bonding jumper. 5.0, if you go all the way to, here's my 5.0. I want you to focus only at the bottom here. It says generator system bonding jumper. Can you guys see that? I have my 5 sets that I already sized for the ungrounded conductor. Multiply them by 600 kcm each. Multiply them by 12.5%. Exactly like the supply side the system bonding jumper or the main bonding jumper. These are the rules. And you get you this number, 375. Do they make 375 kcm in the industry? If you don't know, before you call somebody and ask for that size, go to chapter 9, table 8 in the NEC book, and it will go to the next standard, 400 kcm. Or Southwire, I don't know if they're still in business, Southwire will make this size for you for an arm and leg, right? So 400 kcm, that's your system bonding jumper that you're going to take the neutral to the ground, bond them together. If the manufacturer of the generator already sized this one for you guys, you don't miss it. You are listed equipment inside the equipment, no missing with it. So that's my system bonding jumper for the generator. What size did we come up with? 400 kcm. So my system bonding jumper is 400 kcm. Now, and we size, then we're going to take the grounding electrode conductor here, either to a ground rod next to the transformer or back to the grounding electrode system. So 3.1, guys, let's go to 3.1 for the generator. Did we do that? 3.1 for the gen. That will give me, here's my generator. Same thing, 5 sets, give you 3,000 to 50 to 66. Do not go larger than 3 out. So no matter what. No, not do not. You do not need to go larger than 3 out. Any comments, guys? Any questions about sizing the grounding electrode conductor for the generator? That 3 out could be tied to a grounding rod next to the equipment, or it could be taken all the way back. If your generator indoor, what they do with this, they take the grounding 3 out all the way and tie it to the ground bar, like I did here. Typically, this is for generators. They're indoor. You can see I'm taking my 3 out all the way back to the ground bar, which is tied to all the grounding electrode system inside my building. Yes, sir.
Does it not apply then that, okay, so
in a generator that size, most likely it will be inside the building and tied to the grounding electrode system. If your generator is outside and you're tying solely to the ground rod, you don't have, the code still say you do not have to go larger than number 6. There is nothing that I know of that separated drive system is an exception. Anybody have seen anything? Nothing that I know of. Most of the stuff that I was involved in, really, we don't do the drive rod. They're bigger systems. But anyway, if you were to get up with 6 or larger, that's most of the smaller generators are 6 will be good enough for them anyway from sizing. When you get a bigger, like 1250 kW is a big boy. These are typically in a room in an enclosure and tied to the grounding electrode system. And we actually, when we design them, we go even bigger. Engineering-wise, we go bigger than I've never seen at that size with its number 6
yeah.
to the ground at that size.
One application I'm thinking of is like a rental. You have a huge generator, for example, like that. You drive a ground rod, and it's supposed to be rated with number 6, something like that. Instead of number 6, just you got a generator that's going to be there for a while.
Horrible generators. Yeah, horrible. 250, like 250 kW size.
Sure.
Yeah. Yeah. Number 6. Yeah. Number 6, if it's solely just to the ground, number 6. Yeah. Yeah, absolutely. Number 6. Number 6. Number 6 is your bare minimum. Permanently installed, we go larger than that. Unless I'm not aware, unless I'm missing something, please bring it to my attention. There's so much. Yes, sir.
You said you have the option of bonding or not bonding the neutral in that generator.
Yep.
If you don't bond it, you're still bringing a neutral conductor, or you'll be bringing three-phase conductors.
If you don't bond it, if you don't bond your neutral, you still have to bring your neutral though. If you don't, if you're running, can you hold your system? You're running this is a separate drive system. We're running a non-separate drive system, right? Is that your question? So we're not bonding the neutral here.
So if
You still have to, either way, you still have to have neutral.
if you don't bond the neutral, it's not a separately derived system.
If you don't bond the neutral to the ground at the generator, this is a non-separated drive system.
Your generator always has a neutral in it.
Yeah, you have to have neutral. Regardless if you have a separately, if you're running separate drive system or non-separate drive system, your neutral, your generator that's feeding a grounded system back to the system. You have a gen which is 95% of the time. You have a generator that feeding a grounded system. You're not feeding a delta, right? You have to have a neutral.
I've seen drawings where they have a generator and they're only bringing three-phase wires to the.
That's 13.8. You're talking maybe about 13.8, like 13,800 volt high voltage, or a delta generator, ungrounded
Delta
system.
generator.
Yeah. So you're feeding delta.
Right, so they're bringing three-phase conductors into a grounded system.
You're bringing. No, you can't.
You can't.
You're bringing a delta. Well, yeah, you can if it's separated off. It is separated off system. It's delta anyway, because you don't have any connection. If it's a delta, it is a separated off system. You can bring whatever you want to bring, right? If it's a delta, there is no neutral, so we're not bonding a neutral to anything because the neutral doesn't exist. And when you flip the two phases from this system to this system. So it's a separated off system. Delta, do you guys use delta generators? You saw delta generator?
Well, I've seen plan drawings that have a generator and an automatic transfer switch, and they're only bringing three-phase wires into a grounded system through an automatic transfer switch.
Was it single phase or
Yeah.
Three-phase.
Oh, that's a good point.
Three-phase
Yeah.
480.
I don't know what's in their mind, but I've never seen it. Doesn't mean it doesn't exist. Unless it's a delta, the only thing I can think of. Or the designer forgot to pull another wire on the fan. So anybody, am I missing anything from anybody? Yes.
Last dinner that I was on, we didn't need a neutral in the building, it was 480 wide. We bonded it there because the generator needed to be bonded, but we didn't take a neutral in the building.
Oh, we're not utilizing the neutral.
Right.
Yeah, but did we bring it to the first disconnect means and bond it? You did, didn't that? The generator, the circuit breaker was there. Yeah, in the generator. That's your first disconnect means. You're not utilizing the neutral. Yeah, if you're not utilizing the neutral, sorry, thank you, Jeff. If you're not utilizing the neutral, meaning you're not tying anything to the neutral, all what you're feeding is three phase, nothing is single phase. Then, yeah, you bring it to the first disconnect, which is typically on the transformer. You bond it there and leave it.
Your utility, your service already has a neutral in it that's bonded. Now, if your automatic transfer switch is between the service and your, between the transformer, let's see how it's the service, your automatic transfer switch is after the service. You have a neutral in that service, and you bring three wires from the generator in there, you still have a neutral in your service.
Good point. But now the service is out. Done. Right? We lost the service. We're running on generators only. Where would the current, the neutral current go? It's going to go back to the source. The only way if you don't bring the neutral, the only way the neutral current is going to go back to the source through the grounding electrode conductor and the ground electrode system, which is not acceptable.
So you're saying if you have a grounded system, you always need a grounded system transformer, generator.
If you are to utilize the grounded voltage, if you're feeding three-phase only here, like Jeff said, we're just feeding three-phase pumps only, and our auto transfer whip is tied to a panel that has three-phase only, power panel, only three-phase. We're not tying anything that's phase to neutral. Then you don't have to pull the neutral.
But if anywhere in your normal system.
In your normal system, you're running a,
neutral.
yeah.
A generator would be.
Yes. Only if the generator is utilized, meaning as if you're tying things to the generator. Because the neutral is supposed to carry the unbalanced current in the three phases. If everything is three phases, everything's balanced, right? There's nothing to go back to the neutral. If you tie one line to 277, then the other current is going to go back to the neutral. If you don't have a neutral, no problem, it will work. But the current is going to go back from here through the grounding electrode system back to the source. So,
Something wrong with that flash off.
email it to me. Email it to me. Let me see. Maybe.
Three phase, they don't have a single phase generator for, emergency lighting and, some emergency items and stuff like that. So maybe, it's a three phase facility, but they only need a single phase backup power. So that's why they send three wires.
Okay, that could be too.
Wastewater treatment.
Plant. Okay, these are 48277. Okay, email me. I'll be interested to look at it. I really do.
Perhaps a three-phase power plus lighting and whatever else.
I might be missing something, but that's how I think. I would love to look at it, see if something. Okay, so we size the neutral, guys. We bonded the neutral to the ground. We size it. We took grounding electrode conductor all the way back. The last thing that you need to do is that 4.2. 4.2 is called supply side bonding jumper. Believe it or not, supply side bonding jumper. But before I put that one, I want to warn you, if your generator, like the one that you did, Jeff, if your generator has the circuit breaker sitting right here, like the one that we did that a lot of them do, circuit breaker sitting right here at the generator, then this wire becomes an equivalent ground conductor. Depending on where you put your circuit breaker is sitting right here, then this is a number 7, basically, an equivalent ground conductor. And size based on the size of the circuit breaker. If your generator, like a major equipment, your generator does not have, when we parallel them, does not have circuit breaker here. You pull these conductors all the way to the switch here, and the first circuit breaker you put is right in the switch here. When we parallel generators with big stuff, then this conductor becomes a supply side bonding jumper. And what's the difference? Is the size is different. Okay, can I emphasize the word is, where is your circuit breaker? Does the generator have a circuit breaker on it, right? At it, like a lot of JC generators do. They have a circuit breaker right there. You pull the feeder. When you pull the feeder out of that circuit breaker, then you are dealing with an equivalent on a conductor. And you size it based on the circuit breaker. So my circuit breaker here, the 2000 amp, is right at the generator. I am like on this size. Then I will size the conductor based on 2000 amp. If the circuit breaker is right inside the switch gear, and I'm pulling just a feeder between the two, like we do in bigger systems, parallel switch gear, then this conductor is called supply side bonding jumper. So let's do it as supply side bonding jumper, guys, 4.2. And if you go to 4.2, here's my 4.2. My 4.2 is a supply side bonding jumper, separately drive system. Exactly you size it, same as system bonding jumper and 400 kcm. Is that what the 4.2? And I added here, guys, I added very important thing here. Non-separately derived system generator. It doesn't matter if separately derived system or non-separately derived system. If your system is separately derived system or non-separately derived system, if your circuit breaker inside the switch gear, that wire is called supply side bonding jumper and its size as 400 kcm. And all this stuff is right in these articles. The only difference, if you put your circuit breaker right at the generator, then it becomes a circuit. What do we call it? An equivalent grounding conductor. Becomes an equivalent grounding conductor. Any comments, guys? Any questions? Equivalent grounding conductor. What size equivalent grounding conductor would we need for this? Okay, I'm going to impress you with that one, guys, and go size it based on this. Shall we try it? Anybody want to size it? Here's a calculator that I told you. Let's go size the equivalent grounding conductor on that. Set this one to 75. Okay, so my equivalent grounding conductor what 200 2000 amp. How come that I can't see the bottom of it? Okay, I can't see the zero here. So let me see if I can move it up a little bit or size it. I use a lot of, I can't size it, see it here. Okay, so if we have a 2, I can't, where's the 0? 0 is down.
Hide your toolbar.
Height of my toolbar.
Pokemon.
Okay, minimize this. It's not getting me
Click, see if you can click on that toolbar and hide it.
here, this one.
No, the bottom one. The bottom one.
Oh,
Right click it
yeah, I don't.
where there's not an icon. Right.
I have a lot of icons though. I don't want to mess with that. Okay, sorry. Oh, that's weird because of the way my computer set. Anyway, can you guys size it? You can if you so if you put let's just say 200 and I don't have a zero, so and 225 5 amps. Can you guys see? Here's a 225 amp set and ground. Here's the for number 4 copper. That's how we size the equipment ground conductor from this one. So anyway, if you guys, I'm going to close it, but that's really easy if you can have a zero. Let's go back uh, into my equivalent conductor here. Okay, so we sized the grounding electrode system. So if the circuit breaker is here, equivalent conductor, if circuit breaker is here, supply side bonding jumper. So that's for semiconductor system. If you don't have a semiconductor system, guys, the only thing that's different now, if your system is non-semiconductor system, the only thing that's different, that number 5 does not exist. Number 5 does not exist. Right? That 5 number exists. No, the back your neutral will sit here inside your generator, and then inside your generator. And then you have to, if you're not using the neutral, well, here's the challenge. Now, say if you don't need the neutral and it's a non-separate your system, you still have to call the neutral.
You still have to.
Yes, if it's a non-separate system, because you have to bond it to this neutral, reference it to the other neutral. If it's a regular system, it's already referenced to the ground. It doesn't matter. You pull the neutral if you need it, right? But if it's a non-symmetrical system, take this piece here out. And now this neutral has to be tied to the ground. How are you going to tie it to the ground? You're not tying it here, so you have to pull it all the way and tie it right here, which in turn tie to the ground, reference to the ground, regardless if you need it or not.
Regardless.
Yeah, if it's a non-symmetrical system. Because you need to bond it. Any comments, guys? Any questions? So that summarized the 12 chapters of the grounding and bonding in one sheet. Any comments? Any questions? Any corrections? Any? So that's I can't emphasize the separated drive system, guys. If it's a non-separated drive system, then this number 5 disappears. Then you have to pull the neutral all the way tight there. If your circuit breaker is here, then this is equivalent around conductor. If your circuit breaker, first circuit breaker is here, then this piece is called a supply-side bonding jumper. Supply-side bonding jumper. Any comments, questions about that? Okay, now the devil in the details. I want to give you guys 5 minutes, and I'm going to go through the PowerPoint presentation, look at pictures and details. So you've got the big picture now. We overwhelmed you with it. Now we're going to go talk a little bit more details, if that's not details yet. All right, 5 minutes. or so. let's go into the devils in the details. So like I said, we teach these guys in 16 hours. We only have 4 hours to give you the big picture. So I hope that diagram that I gave you the big picture. Now I want to go from the beginning with it, talk about what's the grounding and why we need grounding and so forth. By any means, if you have any correction on any feedback on the sheet that I gave to you, please, it's a work in progress. I've been using it, or we have been using it for, my God, for almost a year, 2 years now. And I got a lot of feedback, and I keep incorporating it. If it makes sense, it makes sense to me, I guess. And I check it with the code. So let's talk about the first couple of chapters, guys. This is the book that we're going to be using. We're going to talk about grounding and the general fundamentals, a little bit grounding of not ground. Now this is, remember, 95% of the time is scenarios. I gave it to you guys. Now what happened for these 5 to 10% when you don't have to ground the neutral, to ground the system, so the system is ungrounded or it is grounded. So let's talk about these. Let's go back. So seminar grounding and non-grounding course objective. We'll go over this one. So the only thing that, let me go back to these and go over here. So we talked about, guys, in my presentation, we talked about all these, the grounding and bonding at the service, grounding the system, the equipment, the separated drive system, and the second building. All these, we kind of cover them. I will not be able to go over the 12 chapters in details today. So we'll reach up to chapter 4 or so to go over it. So the NEC code book talks about grounding and bonding for systems, services, feeders, branch circuit, and equipment. And I thought this is really interesting because the first thing you do when it comes to grounding and bonding is the transformer given to you by the utilities. You have a major decision to decide, am I running ungrounded system or grounded system? That's right here. Then after here, you go to your service. Remember what we did all the calculations in service? Regardless if the system is grounded or ungrounded, I have to do certain grounding and bonding in the service. Then you go down to the branch circuits and the feeders and the equipment. So they're really, in reality, that book talks about, for the most part, about 3 different things. Start with your system, grounded or non-grounded, done. Go to your service panel, the main panel. Then you have to do grounding and bonding, regardless if the system is grounded or ungrounded or is grounded. And then you're done here, then you go to your feeders and branch circuits, and you have to do grounding and bonding at the panels and so forth. So these are what the sheet hopefully covered for you guys. And of course, sizing it, you saw how many, we sized the whole thing and the sheet that I gave you, sizing all these systems. Talked about semi drive system, second building, agricultural building. There's a whole chapter. Who asked about agricultural building? There's a whole chapter about agricultural building, so I encourage you to go there. I'm not going to be able to go over it, guys. Swimming pool, I'm not going to do it today. Science, healthcare facilities. Second, we just don't have time. That's where the 16 hours happen. When we do 16 hours, we go into details into all these grounding and bonding. My low voltage guys, the electronic guys, that there's a grounding and bonding for the electronic system. How many of you guys do strictly power limited? The power limited guys? If you're doing power limited, there's a presentation done, probably Jeff, you're familiar with it, by Werner Electric, and by their permission, I get a copy of it, that talks about grounding and bonding for data centers and telecommunication rooms and so forth. And I can't remember at the top of my head the standard that they use, but they go above and beyond what we do in the NEC code book. So it's not unheard of to have a backbone, they call it a backbone, that goes grounding electrode conductor that goes into the data center, that's 4-aught, going to servers, and you're tabbing from that backbone grounding wire into the data center back and tying it to each and every one of these servers with number 1-aught or number 6 conductor or so forth, all fully insulated. And the idea behind it when it comes to electronic equipment is you want to eliminate the possibility of any ground fault or any transient in your system, because any transient in your system, regardless of how small that transient voltage is or current, could burn your server. That costs a lot of money. So grounding and bonding for electronic equipment becomes not just for the ground fault, for the survivability of these very expensive pieces of equipment that we do. So if you are doing grounding and bonding for electronic equipment, I encourage you to go to the chapter that talks about the grounding and bonding about them, or email me. I'll get you a really nice PowerPoint presentation that Warner Electric, I don't claim to be mine, did about that particular topic. Lightning protection, tons of information about lightning protection, guys. When we don't get about lightning, Thomson Lightning, anybody have dealt with them? They design a whole lightning system for you, and they will tell you every 100 feet you have to have a ground rod tied to the ground. So long story short, as far as we're concerned, the grounding system for the lightning system have to be bonded completely with our system. So you find if they have multiple rods, that's why in bigger buildings, we end up having 500 kcm conductor, because 500 kcm conductor tying instead of 4-aught to a 3-aught the code, tying it to the ground bar, because of you have electronics to ground, you have lighting to take care of, and you have power system to take care of. So you end up with a bigger conductor. So just be aware of that. If you see a 500 kcm conductor tied to the steel of a building, they're taking into consideration lightning, they're taking into consideration electronics, and they're taking into consideration the power system. So keep this in mind. Unfortunately, we don't have the time to go hazardous location. In hazardous location, there's a requirement for bonding. You would eliminate in hazardous location any possibility of arcing, right? Class 1, div 1, 2, or 3. Class 1, class 2, or class 3, div 1 or 2. So they do a few things in the 480 that's slightly, it's almost, and I went through it, it's almost like bonding at the surface when you are in hazardous location, class 1, div 1. A lot of bonding, bushings, and so forth. Okay, so electrical fundamentals, let's talk about, this is a few things, guys, about just the fundamentals, about grounding and definitions and so forth. Grounded conductor, equipment for grounded and ungrounded system is a big deal. The shock hazard, everything goes back to 70E and OSHA, right? Why do we care about grounding? If you don't care about killing electricians, you know, like we used to do in the past, you really don't have to worry about pulling an equipment grounded conductor or bonding. If you don't care about burning your building, if you lose a neutral, main bonding jumper doesn't mean anything to you, right? So it's a whole thing. Grounding and bonding is safety. Well, proper operation of the system is the most important thing, and not, well, because if the system doesn't work, it's unsafe. So it has to work properly. So that's why you bond the neutral and so forth. And then it has to work safely. So we'll talk about the difference between the short circuit and the ground fault, design requirements for ground electrical system, impedance, circuit impedance, and basic electrical operation. So let's go ahead and do a few of these. I might have to have my clicker here if you guys don't mind, please. It's easier instead of getting into your way here. Now that we can get into that one. All right, now we're gonna get in, bud. Okay. Well, it will make sense if we turn it on first, right? Okay, my pointer here. So let's go talk to the Ohm's law. I'm gonna go very quick over these guys. What I like about it, if you guys in the electrical business, you know, I always define we're in the power business. That's why people pay you and I, right? Otherwise, what is electricity? Why do we care about electricity? Electricity, we are in selling power, like the electrical utilities. People come and hire us because they want to utilize this very powerful, useful energy that we call electricity to heat, cool, light their buildings, right? So we're in the business of selling power to the customers, or facilitating the operation of the power system for the customers. In order for the system to work, guys, the first Ohm's law, very simple. You need to have a voltage pressure. That pressure, the voltage, when it pushes certain amount of current, the voltage and the current together create something called the power. That's how much power you're going to generate. So you got, here's my voltage, here's my current. In combination, when you combine them together, that's I times V, right? You guys do it all the time. Here's my I, here's my V. You put them together, it created the power that we're going to deliver to this building. Welcome to the power law, right? That's how much you, so if you take this amount of voltage and push this amount of current, you push this amount of power through to the customers that they can cool, heat, or ventilate, as well as light and operate the equipment. The principle of operation, guys, is as you push the energy through the building, it moves in the form of current. That current faces resistance, and that will come to the Ohm's law. That's your Ohm's law, V equal I times E times R, or V equal R times I. And then in an AC system, in a DC system, then in a DC system, all what you're looking for at R, in an AC system, the impedance takes the form of inductive and capacitive reactance. I don't know, bothers you guys. What the heck is in capacitive reactance in a conduit that's carrying three conductors and a neutral of 277? You have 3 circuits, right? 3 circuits, 20 amp each. 277 lighting circuit, 3 circuits, 3 hot phase A, phase B, phase C, and a neutral multi-wire branch circuit in an EMT conduit. Now and it has an inductive reactance. What type of inductive reactance is this? As you loop these circuits, right, you're looping these conduits, you're going up and down and all four. Every time you loop a wire, you create this so-called inductive reactance. It doesn't have to be that big, it's not a coil, but every time you loop that wire, you created an inductive reactance. Who cares? Believe it or not, every time you loop the wire, you actually slowing down, pushing the energy inside your building. You're creating inductive impedance into your system. That's your inductive reactance of our system. Same thing, take your EMT conduit with 4 conductors, number 12 THHN in it. They're burning at 277 to ground, right? Now, if you look at the wire, guys, your conduit is grounded, right? EMT conduit is grounded. And you put inside the conduit a wire that's hot, right? So here's a 0 level, and here's a hot 0, 277. And in between them is air and insulation of the conductor. Isn't that the definition of a capacitor? What is the definition of a capacitor when you guys went to school? The definition of a capacitor is 2 plates, one of them is sitting at 1 voltage, the other is a different voltage, and in between them is dielectric insulation. Well, we'll come to what they call it the capacitive reactance of the power system. That's how you get your capacitive reactance of the power system. I always, and don't let me be carried away because I'm a power engineer. Even we see all this thing, guys, but I will remind you, 95% of your impedance in any power system is created by the offender, the resistor. Regardless if we talk about XL and XC and all this stuff, but still, 90%, that's a substantial amount, 90% of any AC power system, impedance is created by the R. But the other ones, all of the others constitute that 10%. So the R, and what R is? R is the material that you use. Copper, the bigger the conductor, the smaller the impedance. So you can control R easily because you can always reduce R by pulling bigger conductors. So if you can control, that's why we have bigger control in the power system by bigger conductors. We can always size conductors bigger, and we have a full control, like voltage drop. Voltage drop, when we take this one, 90% of the offenders when it comes to the voltage drop is the R. So how do we solve it? Size the conductors upper. So we're good up to 90% of the power system. Okay, you guys have seen the wheel and all what we said. I always say, if you're in the power industry and you don't know a couple of these, you probably should find yourself a different career. The watt, here's the power. This one is the most important thing. That's how much power we can push into the building. The current times the voltage. Here's my voltage, here's my current, pushing it in. That's how much you get your power. That's the watt, E times I. And the ER, this one is Ohm's law. So these are the single most important two formulas when it comes. This will get you the resistance to the current. This will get you how much current. If you get this amount of voltage to push this amount of current, that's how much watts you put into your building. Any comments, guys, about these first concept? That's how the power works, and how later, well, the reason why they start you guys with this, because grounding and bonding is a circuit. It's called safety circuit. So at one time, you're going to have this resistance in the ground path. So you have to have this conductor large enough to facilitate the operation of the overcapacity device, meaning to allow bigger current to go right through it fast enough so that circuit breaker trip before you burn your building. Right? Does it make sense that your circuit breaker tripped after you burn the building or before? If you don't care about the circuit breaker tripping after the fire truck pulls in, then you don't have to worry about the grounding and bonding. Okay, this is just a couple of examples, guys, how to find the Ohm's law and so forth. I want to emphasize basic principle applied to the normal electrical circuits and the grounding and bonding circuit. We're interested to Ohm's law, the whole circuit that you did. The higher the impedance, the less current that you can push through it. That applies to the normal operation of an interactive unit, full-top unit, light, as well as the abnormal operation of equipment. What's the abnormal operation of equipment? You have a ground fault right here. All the current is going to bypass, cut through it here, and goes right through that short circuit of the ground fault all the way to the source. So if that conductor is not sized enough, it's not going to allow the current to go fast enough, large enough through it to facilitate the operation of the overcapacity device. So Ohm's law, guys, apply to normal operation of equipment as well as abnormal operation, which is short circuit and ground fault. So just keep this in mind. We call the circuit, I'm going to emphasize grounding principle apply to, like I said, normal and abnormal operation, which is grounding and bonding. It's called the safety circuits. All the green stuff that I showed you guys, all the grounding and bonding, it's part of the safety circuit. Safety circuit. For example, look at that. Current takes the path of least resistance. Current will be present. These are all applied. Current will be present in all paths of the circuit. Where more than one path exists, current will divide. This is normal operation of a circuit, right? And at the same time, abnormal operation. Low impedance circuit or path will carry more current. Normal operation, parallel series circuit, right? Remember the parallel series circuit? That applies to the normal operation as well as the safety circuit. This is a good example. The higher the impedance, the lower the current. Higher impedance, can you see? Lower current. If the impedance starts going down, the current going up. That's why they don't allow us to depend on Mother Earth as a return for our ground fault, right? Why? Because Mother Earth could be high impedance. What happened with high impedance? Lower current. What happened with lower current? Circuit breaker wouldn't wake up. He wouldn't see it, right? Before it starts arcing and sparking and burn the building. So that concept of the higher the impedance, the lower the current, very powerful for many reasons. For the safety guys is we need our path to be low so our current can be high so circuit breakers wakes up and trip and save my building from being burned. Multiple paths. Back to who said that we in the agriculture building we used to bond the neutral at multiple buildings in the past. That's why they don't want you to bond the neutral at multiple buildings, because if you're bonding right here at building B and the current is going to building A here, so every coaxial cable, the shield of coaxial cable, every water pipe, every conduit between the two buildings will be carrying current under normal operating condition. Isn't that scary? So you have the coaxial cable that going from building A to building B carrying a few amps, taking it back under normal operating condition. That's why we don't want us to bond the neutral other than in the service. Same thing guys for the grounding and bonding. When you ground and bond everything together at both ends, you are creating parallel paths. So the current will go in each and every one of these paths. And I keep emphasizing the word normal operating condition when the power system is running and the air handling is up and running, and under abnormal condition when the circuit is in a ground fault condition or in a short circuit condition. Okay, here's overcapacity device. Look at this normal operating condition. The current goes from the service through a conduit to the second panel. Burn that Chad Curtis plasma TV here. I don't know, my smart TV, my wife's smart TV. Coming back here all the way to the source, and everybody's fat and happy, right? And see, now the neutral is facilitating the operation of the equipment. Everything is cool. We bonded the neutral to the ground here. We ground the system, and everything is as good as it could get. Okay, now what happened is we have a ground fault right in this situation, right? And remember, the box here is also bonded. Now we have a ground fault in this situation. When you have a ground fault, look what happened. Now we bypassed my plasma TV, my smart TV here, because of my smart TV has a higher impedance. I have a parallel path between going through my plasma TV high impedance and my very low impedance ground fault path. So most of the current will go right through the enclosure as your equivalent drive conductor all the way to the source. Your job and mine is to make this path Highway 494 or 35W, not the alleys of Minneapolis. Does it make sense? Bigger, so the current guys go faster. Depending on the overcome, that's why we use the overconduction device, because that's the valve that's going to allow how much current ground fault to go through. If that's high, the equivalent ground conductor have to be also size appropriate. So you can see what happened to the ground fault. It goes all the way back to the source. 99.9% of your ground fault is going to come through the conduit or the equivalent ground conductor. Right in here, guys, takes a free ride over the neutral. That's why we bond the neutral, because we're going to go to this reference point right here. We bond the neutral, so it jumps, take a free ride over the neutral in the service back to the source. Now, that's 99% of it. There will be close to 1% goes through Mother Earth, especially in Minnesota when it's wet, right, and really, really good low impedance here. You'll have some current going through here. The NEC code book said, ignore this. This does not exist. We don't want you to depend on this. But let me tell you when this becomes very powerful. What happens if you lose a neutral here? Well, in this system, it doesn't matter, because if you lose a neutral, you lose the whole circuit. But if that was a split phase system, there's another phase here, and you lost your neutral here, right? And you have a ground fault, your ground fault will all go right through Mother Earth. We're not supposed to, but that could be kind of your second line of defense at one time. For your ground fault, if you lose a neutral, what happens if you lose your neutral right here, guys? Go cut the neutral now. Do you think your power system will work? Anybody want to try it? Go get rid of the neutral. There is no other phase, which is safer here. That's how they use it in Europe and all over the world. They use 220 here instead of 120. They use 220. Everything is a one hot and a neutral coming to the house. So 220. If you lost the neutral, what happens? If you lose a neutral, and if you lose your neutral, your system here, in this case, you will continue to operate. Here, you continue to operate because you're bonded to the ground. So the unbalance will go right through the Mother Earth. Obviously, we don't want to depend on it, but that could be your second line of defense if you lose a neutral instead of burning the building. That bonding here becomes your second line of defense. Okay, so we have normal operation of overconduction device. Look at that, beautifully going, cooking that equipment. Your equipment ground conductor is right here. This is how much current based on the impedance of that load that you can pull. 1.5 amps coming out of a 20 amp circuit breaker, it can go forever without tripping it. The minute that you short accidentally or intentionally, like Chad like to play with it, you can go grab phase A or whatever hot one, make hot one touch the equipment, you bypass that impedance, the current will go right through the equipment. The easiest path would be through the equivalent ground conductor all the way. Right here takes jump over the neutral. Can you see it? Free jump over the neutral back to the source. Now, since the impedance of this path is very low, 0.5, look how much current out of this circuit breaker is going to come up. Very high amount of current. This guy will wake up and trip. That's the fundamental understanding and operation of an overconduction device, which we're going to be doing in the second segment. Why do we have overconduction device, and why do we care about this conductor be as large as possible compared to the overconduction device? So facilitate the operation of the overconduction device. Any comments, guys, about this? Comments? Can you see why I started you with that big picture first? Otherwise, you get lost in the details. Here. So straightforward. A couple of definitions. Ground is Earth. So when we invade the moon, we have to redefine what ground is, right? And inhabit it. Grounded or grounded conductor, you're going to hear the word grounded conductor intentionally tied to the ground, or grounding. Connected, the word that we use, connected or connecting to ground or any metallic object to extend the existence of the ground, like that ground bar that we put at the bottom of in the electrical room to tie to it. Bonded or bonding, connected to establish electrical continuity and conductivity. It used to confuse me all the time, guys. One conductor can act as an equivalent grounding conductor and a bonding conductor at the same time. So don't get it. Like if you look at the take an EMP conduit between two panels, 4-inch EMP conduit between two panels. The EMP conduit will act as an equivalent wire conductor by code approved to certain distances, which bring us with how far can you pull an EMP conduit before it's no longer qualify as an equivalent wire conductor. Did you guys hear that there's distance limitation? That book goes about the distance limitation. How far can you pull a 4-inch EMP conduit before it loses its ability, increase the impedance. So the code, there's a couple of tables at the end, a couple of hundred feet, then it becomes too high impedance, then you have to pull an equivalent conductor. So it's interesting. So connecting to establish electrical continuity. So that pipe acts as an equivalent ground conductor, and at the same time, with the lock nuts, acts as a bonding, that bonding this enclosure to this enclosure. So grounding and bonding almost give the same function. When it becomes a big deal, different like bonding conductor, you have a piece of equipment with a 20 amp circuit coming to it, so you bring hot and neutral to it, and you have an equivalent ground conductor tied to the, let's just say, I don't know, a fan in a tank, right? And the tank is also bonded to the frame of the fan. That's now we're bonding it together. So with a wire, and we're taking with an equivalent ground conductor all the way back to the source, all the way back to the source. The difference between the grounded conductor and everything else, the grounded conductor, the neutral guys, is essential part of the normal operation of the power system. Essential part. You can't, if you are to utilize neutral voltages, line to ground voltage, 120 or 277, you must pull a grounded conductor. So that's why, yes, it's part of the grounding system, the grounded conductor, but it's really an essential part of the normal operation of the power system. So we talked about grounding in the service and similar system. Not permitted to use the grounded conductor, with some exceptions, as a grounding conductor. With a few exceptions, remember that range in the old days and the range replacement, they allow you to do what? To use the grounded conductor, the neutral, as an equivalent grounded conductor in an existing range. Dryers, that was an exception. On the farm, feeders, if you're going to a separate building, they allow you to use the grounded conductor. So if you have a 3-phase system, you run 4 wires, 3 phases and neutral, to the second building, knowing that your grounded conductor can be used as an equivalent grounded conductor. No longer valid, except for existing building, like I said. So you have to pull an equivalent grounded conductor. You can't use the grounded conductor as an equivalent grounded conductor, though it works. It does work. Not legally. Yeah. A lot of things work. You can use barbed wire as a current carrying conductor, and it would work. Not efficient though. Equivalent grounded conductor. 250 guys list multiple means or 250.188 that establishes the equivalent grounded conductor specifications. So the equivalent grounded conductor is simply, it's supposed to ground all the metallic objects of any electrical equipment or electrical load that has a metallic frame or metallic box to ground it. But all metal enclosures at each potential along the at each potential at the along the circuit. So if you were to change the ballast on this and it's not grounded, and you're barefoot in a basement in a metallic ladder, so make it perfect shock, and that frame is energized because of malfunction in it, you grab into that frame of that light, which is metallic, current goes right through you. That's what we call the perfect shock that sends you to the Lord so fast. So the smarter than Chad said, what if we grab a wire and tie it to the frame of that fixture, right? That wire is called equivalent ground conductor. Now, if that's to happen, then the hot will touch the frame. The frame is already grounded. Bang! It gives you a low impedance to the back to the source. The circuit breaker will wake up before you get electrocuted. That's really the fundamental need for the equivalent ground conductor. That's why you need the low impedance to the ground. Facilitate the operation of the overconduction device is a big deal, guys. Number one, how many of us walk into basements? Remember the old refrigerators, non-grounding type refrigerator? When you touch it, you get a little shock, right? So imagine how many people barefoot, like my wife, walk into the basement all the time, opening a fridge. And imagine if the fridge over that 1 year that has been sitting there, accidentally something malfunctioned. Now they have the 120 touching the frame of that fridge. Now you're looking at a hot 120 to the ground, barefoot basement. Let's make it in the summer when it's wet. So that's what we call the perfect shock. That's when we ground the frame of that fridge to help you from 7TE, the shock hazard, to eliminate or minimize so-called the shock hazard. The shock hazard. And we will talk about the operation of lower temperature device, guys, later on. Okay, purpose of grounding and bonding. A couple of things, guys, you guys are familiarized with that. Limit the voltage due to lightning, line surges, or unintentional. I don't know how many people pay attention to this. Stabilize the voltage to ground during normal operation. Now, grounding the system. Why do I care about taking that 9 volt, taking the negative in the 9 volt, tying it to the ground as I power that bulb that's tied to it? 9 volts not a whole lot, but in a higher system, the most important thing when we tie it to the ground, we stabilize the voltage to the ground. So wherever you go in your plant, you're almost guaranteed to ground a 120, right? Plus or minus 5 or 10%. That's where stabilized voltage to ground during normal operation. So wherever you go in your plant, the voltage between the hot and neutral is 120 plus or minus 5% fluctuation in load. And the voltage to ground on the 120 or 240 120 system is between the pipe and the hot is 120. That's stabilizing the voltage to the ground. Limit the voltage, the transient voltage with the lightning and surge resistors. The worst thing that could happen to you is a high voltage 13.8 line hits the low voltage 240 120 or 480 277 coming to your building from the utility side. You see how the utilities do? They have the high voltage at the top, right? And right underneath them, the low voltage, the secondary distribution system, they call them. And when they do it this way, have you guys noticed that they typically put the grounded conductor at the top? So if that conductor is to fall, it will hit the grounded conductor, so you have a ground fault. So if high voltage touches a low voltage, 480 touches 208, or 13.8 touches 480, it will create the transient voltages inside the building. A transient voltages on an ungrounded system is very destructive, and a grounded system is less destructive. And that's kind of the advantages of line surges, the same thing. Utilities take a transmission line, 138,000 volt from one transmission, switch you to another transmission line, and create that transient into your system. If your system is grounded, it's the ability of the system to absorb the transient if it's grounded is much higher if it's not grounded. Now we'll talk about the advantage of these systems. So bonding. The bonding ensure electrical continuity, conduct safely, any fault current likely to be imposed. The same thing grounded and bonding will do things, guys. The last thing you want to do is you have a tank, a metallic tank with a pump in it, and the pump is isolated, the frame of the pump is isolated from the tank, and the tank get electrocuted, or not get energized by one of the hots because of malfunction, and you go grab one side of that tank, and you are barefoot. I always use a barefoot. How many of us work barefoot? You get barefoot when you work with these equipment. Barefoot, in the mud, wet. That's the perfect shock. You know, wet. Then it will send you to the second line. I've never done it, but you can literally wear your boots, rubber boots, and grab on 277, nothing will happen to you. Have anybody want to try it? No, I wouldn't try it, but as long as you're isolated from the ground, guys, you don't. That's why we wear boots, and you're trying to, when you're working with equipment, the rule, Keljik, is you work with one hand, don't put to the other hand. That's the last thing you want to do. You got tied 277 here. Here's Chad getting the ground from this side. The whole idea, if you get electrocuted, is to interrupt the path of the ground fault. If you interrupt it, you survive. How do you interrupt it? You're insulated from the ground. So if we get electrocuted. But when we ground the system, we do the opposite. We want that path to be so easy. Grounded, bonded to everything metallic. So if accidentally somebody moved this fixture, hot touch the ground, immediately the ground fault will wake up and say, yep, there's a ground fault, go fix it. So that should ensure electrical continuity and conduct safely the current imposed on them. A couple of things about grounding and driving. Like I said, the zoo conduit will act as grounded. That's the conducted by extending the ground connection. Look at this. Is my conduit here. Everything is ultimately everything starts with the ground. Okay, you can see here's the ground. Here's my ground right here. That wire extend the ground to here, and then this wire extend the ground to here. So grounding to the tying everything to the ground. You can see this conduit bond the two together and at the same time also extend the ground to this. So you can see everything is referenced to the ground and my system is referenced to the ground. You're running a grounded system, a grounded equipment, and the two of them are referenced together to Mother Earth. And the two are also tied together through the neutral. Can you see that? The neutral take this ground, that's highway interstate. The highway, like the interstate, let's say interstate 494, coming from here all the way, can you see that, to this ground? Bond the two grounds together.
Question.
Yes, sir.
In European systems, you're not bonding the neutral, are you still using equipment grounds? What's return?
Yes.
What's
Yes.
return path on the equipment ground? Are you grounding your transformer someplace to give you that return path, or?
Your return path, if you are doing, you wouldn't do this on a system like this. So just, well, because that's where you're neutral, that's a problem. That's a problem with the power system that we have here. Is if you lose a neutral here, and you're not bonded to the ground, you have an open neutral, you burn equipment. You burn buildings, literally. But if your system is 220 system like they use, here's my 220 system. Now imagine this conductor does not exist, the second leg here does not exist. So now you brought your neutral to this point, this does not exist at all, you can't do that. Okay, you still have to do everything else. You're creating a grounding electrode conductor, a grounding electrode bar, tying that all your ground is coming here. The only thing that does not exist is that bonding, system bonding jumper. You can't do it. Does that make sense? So if you have a ground fault in this piece of equipment here, I have only one voltage, 220, and 220 voltage can push. The higher the voltage, the more the voltage can push the current. 120 cannot push the current as good as 220. So I have a ground fault here. My only path to the ground is through Mother Earth, and that's acceptable practice. It's going to go to the source. So everything here, and you're looking, I know Jerusalem, but you're looking at rocky mountains there. It's not like Minnesota where you can dig 2 inches, probably 2 feet, and you find water in certain places here. You have to do 2 miles, or you can reach the oil before you reach water there. Literally, if you dig in the mountains. So, but this impedance, the utility comes and they force them to do, here's what they force them. The inspector literally, guys, have ground fault detectors that they put it right here. If you have here less than 5 ohms, more than 5 ohms, it will fail you. They would not approve the building. So then what people do is they have concrete encased electrodes. Most of the building are done with concrete. So rebar around the whole building. This is the best. Concrete encased electrodes are the best electrodes. And you put it up here, and then you tie it to the wire system, which is becoming less and less reliable all over the world with the PV that they use. And between the ground and electrode conductor, they'll give you very low impedance, 5 ohm, and that's an acceptable way of returning your ground fault all the way to the source. Now in the US, we need 25, right? They allow you 25, and most of the NEC code book 25 or less, you don't need a second ground electrode conductor. They don't measure, do you? Unless you do commissioning and buildings, do we guys measure the ground impedance? We don't measure the ground impedance unless you do commissioning and buildings. So there, the inspector, before they approve it, have tools that measure the ground. So 5 ohm isn't acceptable. And it works, believe me. But the advantage of what, I know exactly why we do it this way, especially in single phase system. We use that 240, 120 split power system, which is unique. You lose a neutral, you burn equipment, no question asked. But if I lose a neutral right here, a storm came and knocked down 3 wires coming to the house, knocked down one of them, if you have wires, right? And happened to be the neutral. Could it happen? Or a squirrel chewed right one through the neutral, went to the neutral. So now we lost a neutral. If you don't have this, you literally burn the house. Because all the equipment in your system, everything, your plasma TV, everything that's on at the time will turn into a big fire. You know, now imagine in a house that's made out of wood like we do our buildings here, not concrete like they do there. So that's a major difference, and I understand fully why we bond the ground in a single-phase system. On a three-phase system too, in the three-phase system, what they do there, the reason why they don't bond them too, in a three-phase system, guys, by the time, first of all, no, they don't give you three-phase system for dwellings. You really have to have a villa to get. Do we give three-phase system to dwellings, single-family dwellings here? We don't give a lot of. You have to have a really big house to get three-phase system from utilities. So that's 95% of single-family and two-family dwellings are powered with single-phase 220. Done. So you eliminate the three-phase. Three-phase is apartment and industrial commercial. At that level, when you have apartment, industrial, commercial, when you have multiple loads coming together and you lose a neutral, there is enough load in the building to balance it between the three huts that you wouldn't burn. It would act wacko though. You will still, the light goes up and down, and but enough load balance not to burn as much buildings. Put it this way. Still, you want to solve the problem, shut down the system. Any comments? Any questions? Comments, guys? So that's your bonding. If you can see grounding, can you see the same system? These two are bonded together through the conduit and the bushings here, and grounded together, right? And this conduit is grounding this piece of equipment to the grounding electrode to the grounding system that you have here. So bonding and grounding almost interchangeably in a lot of applications. Any comments, guys? Any questions? Comments? See, I'm bonding the frame of this air handling unit to the frame of this panel through an equipment grounding conductor, or it could be the EMT conduit, or so forth. Any comments, questions, corrections? You guys are still awake? Well, that's good. Okay, so let's go there. So with that, okay, there we go. So grounding compared to bonding. This is just a couple of, when it comes to bonding, the only thing I can think of, like bonding, almost uniquely bonding, is the main bonding jumpers, right? These are kind of almost uniquely bonding. For example, the main bonding jumper here, it does the work of grounding though, but it bonds the neutral to the ground, to the enclosure. When I come from here, supply side bonding jumper, you guys remember the supply side bonding jumper here? It's uniquely bonding, supply side bonding jumper. System bonding jumper, uniquely bonding versus grounding. Equipment bonding jumper on the load side, equipment bonding jumper on the load side. So this is pipe, and I'm bonding this pipe to this enclosure, even though I'm putting an equipment ground conductor inside it. By the way, we're not here, but even though if I put an equipment ground conductor here, I still have to bond the enclosure to the pipe. That's where bonding becomes kind of slightly different than grounding. Any comments, any questions, guys? Corrections? Okay, effective ground path. Why do we care about making, they keep talking about effective ground path, guys, taking it from here through this conduit, through the frame, through here, back here. Now here, it takes I call it free ride through the enclosure back to the source, versus going back to Mother Earth. Must be the ground path, that path effective. It is the safety circuit. That circuit acts under abnormal condition. They call it the safety circuit. Under normal operating condition, your equipment grounding conductor doing nothing. By the way, IEEE standards, I read in some of their standards, 85% of your faults in any power system, anybody can guess what's 85% of the faults that we encounter? Three-phase, phase-to-phase, or ground faults? Ground faults. How many of us grab phase A and phase B, bolt them together, and flip the switch? How often do you do that? But how many of us go monkey around with a ballast like this and accidentally the hot touched the ground because it got loose, especially when you work energized, when you're not supposed to work energized, but you're lazy like Chad and will shut down the system. Right? How many of us stand there and try to move it away and tie it with a wire nut and accidentally touch the frame? So ground faults account to 85% of your power system. So if you can solve, and the equipment grounding conductor is the safety valve so it will save you 85% of the time. The ground fault is your safety set. And what happens to the other 15% of the time? what would happen? Well, if you're what could happen is the three-phase bolted three-phase system. Say if you are part of lockout tagout procedure that you have to do in medium voltage system. At the end, the last step that you do in lockout tagout procedure is take phase A to phase B to phase C to the neutral bar and bond them with a bonding cable. That's required, recommended in 48277, required on anything higher than 600 volt. So what happened now if you forgot, which happens in stories? Or people forgetting, now you worked on it, de-energize it, right? De-energize, put it in a safe working condition, you came back to an energizer system. You forgot that you put this bonding jumper. And it did happen, believe me, it did happen. And I know of a scenario where it happened and you flipped the switch in the 13 years. Now that you got yourself face to face to face short circuit. That's the scenario they would have face to face to face. I can't think of anybody who will have to, even when you drop a wrench inside the switch gear, you typically take either face to face or face to neutral. Face to face to face, which is the worst scenario, is highly, I would say, less than 5% of the time that you encounter it. And we size the equipment, by the way, to handle 5% of the time. So things are sized to handle that 5% of the time. So your chances of having a face-to-face short circuit in the building is probably 100 times less than your chances of being hit by drunk drivers driving in Minnesota here around the holidays. But we still size for it though. The path must be electrically continuous, fat enough to facilitate operation of the overconduction device as well as the flow of the current. So continuous, you can't have it, current is not going to jump around, and it has to be large enough so the current can go fast enough through it to facilitate the operation of the overconduction device. Circulating current, you hear a lot about keep the current on the path intended for use. That's what they talk about circulating current, multiple grounding connection to a grounded, can you guys see the word id, grounded, the neutral, downstream the side, that's why you don't bond the neutral. Keep the grounding connection, let's go directly to here. So look at this, here's my plasma TV here. I'm taking my service 200 amp to 100 amp to 60 amp panel all the way to a 20, 15 amp feeding my plasma TV. The current under normal operating condition, as it should, goes right through the hot, right through the neutral, back to the source. That's how the system should work properly. I am bonded, my neutral is referenced to the ground, which the service is referenced to the ground. All my equipment are bonded together through the conduit. That's typical safe operation condition. Now look what happened if I send one of my friends to go there and they bonded the neutral at multiple locations, right? Now you have your coaxial cable in this area is carrying current, right? Because the shield of coaxial cable, it could be bonded in both ends. Your water pipe is carrying current. So you can see the conduit now under normal operating condition. This is not short circuit, that's normal operating condition, like this. This power system above your head light is normal operating condition, right? There's no short, no ground fault that we know of. So the current is going right through wherever. That's your so-called circulating current, and that's what you will eliminate when you bond the neutral once at the service. Any comments, guys? Any questions? So even the current goes right from our earth here. So if this is a separate building and you're supposed to create a ground rod right here, grounding electrical system, you don't bond the neutral again. If you do, then the current will go through the earth. And what's wrong with this? What's wrong with this? Question would be, what's wrong with this? Well, safety, you could have your plumbers coming and you're working on water pipe and they open the pipe and it arcs, right? Because it's carrying current. So hazard. It could be, if you have flammable things, it could be that arc could create, if it's in a hazardous location, create a fire. So the safety is your low voltage guys work on low voltage equipment and they get shocked by the coaxial under normal operating conditions. So that's what you will avoid. You avoid this one by what? By only running the neutral on one side. Any comments, guys? Yes, sir.
Go to your next slide, that one there. Let's say you've got an equipment rack plugged in to panel 2 that's a metal rack sitting on concrete. And inside that equipment rack, you have gear that has a neutral, they're tied inside the equipment rack. So you're effectively doing
yes.
that.
Yes.
Even though you
electronics, they got the neutral, I mean,
Yeah.
all the gas things tied, so you effectively have that problem.
Yes.
You
Yes.
got a steel foot rack sitting on concrete, inside the foot rack, you've got stuff tied to, where the neutral's tied to ground, inside the gear.
So you take, what's the amp, like a 20 amp going to that equipment or higher?
Well, I mean, you might have 30 pieces of IET equipment inside the rack, and each one of them is tied to ground, and then that steel foot rack sitting on concrete, so you have that problem.
Now, tied to ground is one thing, tied to neutral is a completely different thing. So here's your server. That's where we're burning your server here. So this is, we're burning the server at 120. The power came to the 120. You see that neutral here? That neutral shall not be tied to the frame of that server. The neutral, that wire here shall not be tied to the frame of the server. But you still have an equipment grounding conductor going to your server though. So if I have my green here coming in, so I have my server coming in here, going to my equipment grounding conductor right here. So that's, I don't know if you're talking about this wire, the equipment grounding conductor tied to the frame of that server, completely isolated from the neutral. Now, if you have a wire inside your server that tie the two together, now we got a problem. If you have a wire that thick, that's what happened, right? Yeah. Yeah. So that's what.
So we have that happen all the time. So what we have to do sometimes is take that equipment rack and isolate it.
Would the equipment malfunction then?
We actually, and that's why we use isolated ground outlets inside the rack, and we use plastic sleeves on all the metal conduits and actually isolate the rack from the cement with the pad. Otherwise, we get that problem all the time, where you get voltage on the coax or voltage on the Ethernet cable.
Yeah. No, I hear you. When it comes to equipment, there's grounding electronic equipment is and the other thing is when you take this one into the server, now you take it even further here and you take it to different voltages, right? I don't know what 24 volt or whatever, you take it inside to convert it. And so now that these equipment on this side is also reference to the ground. You know, the electronic equipment is reference to the ground, the chassis ground they call it. So I can see that. So if you came, yeah, that could be a circulating. So what you do is you isolate the system then.
Yeah, you have to isolate the whole equipment from ground, which is really weird to think about, but we have to do that because a lot of the electronics they're tying the neutral to ground inside some of these pieces of
And then that's legit in an NEC code book, and it's still safe. So what you do is you take this, they allow you the code to take a one isolated ground all the way up to here. And that's legit, that's completely legit. And that isolated ground, that's at the load level. You're not into our panel, you're not in the electrical panel. At the load level, and most of the equipment are plugged in, right? Plugged in, and the isolated ground is tying you're tying your equipment to the isolated ground as well as your rack is tied to the isolated ground. Nothing wrong with that. Then you eliminate the circulating current. At least in going through the yeah. And that's why the whole idea of isolated ground came to be. Yes, Jeff?
Somewhere in any shock hazard, if you tie those neutrals to the frame, to the body, and any shock hazard, you touch the panel, service panel, and then grab the panel board, is there any possibility to go to the critical to the ground system?
Well, ultimately, everybody's tied together here, right? So I hate to go to the high voltage. In the high voltage business, like 13.8, if you move from here to here, I can't remember, 2,000 feet, which is really high distance, 2,000 feet or 3,000 feet or so. If you move from this point to this point, something in the thousands of feet, the voltage between the ground and the neutral start going up the further away you go. On the low voltage system, it's not an issue. In the high voltage system, that's why utilities, when they go on the power poles, every 2-3 power poles, what do they do to the neutral? They ground the neutral again. Force the neutral to go back to the ground. Because the further you go, the impedance goes bigger, and you could create a voltage difference between the neutral, which is grounded at one point, and the ground at 200 feet away. You could create like 400 volt difference between them, enough to kill people. I don't see it here though on a power system, construction power system, because that's you're bundling this is equipment, electronic equipment. You're taking it here all the way through the grounding system and taking it back to the source. But that conductor could be carrying current though, the equipment ground conductor. But did you say that even though if you do it, you get rid of this little bundling here, or you keep it for your operation of the equipment?
So racks getting its ground, there's an isolated conductor all the way back to the
Okay.
building.
Fine, but what happened to the actual? Okay, that's coming through the plug though.
Yeah.
That's coming. So the rack is going all the way back, and this one is also coming from an isolated ground.
Yeah, actually, the rack has a plastic sleeve in it, and it's completely isolated. physically
From the ground.
From the ground. It's only getting its ground from isolated ground, so it goes all the way back to the building's main grounding pattern.
And that's back to the proper operation of the equipment that you guys are working on. And that's they're all bonded and grounded right through at the level of the service though. I don't see anything wrong with that one. But still my point is here, inside the equipment, do they take the neutral bonded to the frame of the equipment? Some. Yeah. Well, see, the problem, I used to say by design, but some of these electronic equipment, to work and operate, you have to do that. That's where the,
Like a lot of the UPSs would isolate. The load would be isolated from the line.
yeah.
Because
Then you get-
they're through an inverter or something, so you no longer have
Yeah.
a connection from the neutral to your.
So they have an isolated power system here. I don't know
Like
if
a
you,
UPS,
yeah,
you do
yeah,
have to run
yeah.
an inverter. I mean, it's just like
Yeah.
a transformer. You don't
Completely
have-
isolated the two
You
systems,
don't
yeah,
have a physical connection anymore.
yeah,
So that should eliminate some of the potential.
yeah.
Or a one-to-one.
I'm sure if you take this circuit here, I mean, your electronic equipments are not really working on 120 or 208, they're working on a lower voltage, the server. So if you take an isolated transformer right here, inside the equipment, and take it to, convert it to a usable voltage in the other end, yeah, I don't want to get carried away, but there's so many ways inside the equipment that you can do. But I heard it though, with the electronic equipment. Good point. At the equipment level. At the equipment level. Now, what your issue is, if you have a ground fault detection here, you will trip the equipment. If you have a ground fault protection in this system and you do it this way and you're tying it, because the ground fault is looking at the current coming back at the ground, you could trip the ground fault because of that current. Okay, this is just a couple of things, guys, about the layout of the article, Article 250. This talks about general circuits and systems to be grounded. Remember how this is which system you can ground, which system you cannot ground. A system, so systems that you can ground, system is it's up to you to ground. A system you cannot ground, even if you want to. Talks about it here. DC current, if you guys are into the solar photovoltaic system grounding, this section talks about it. If you're in a high voltage system, the whole section talks about grounding high voltage system. I can summarize it to you in two things, two systems, either multiple grounding for the neutral or single grounding for the neutral. That's what they use. So that's the funny thing, on the high voltage end, circulating current, not a big deal. So you can take the 13A, bond it at one location and bond it at the other location, bond the neutral at the other location. Luckily, in most of the building that we use, guys, we do not use the neutral over 13A. What we do, utilities do, we take 13A like in hospitals, phase A, phase B, and phase C, only with the shield of the cables. Just the shield is to shield the cable. We bring them to a switch gear. We bond the shield from one end to the switch gear, no neutral to be seen. You bring it to a delta transformer from one side, no neutral needed. Take it back to convert it to whatever voltage system you need. I was involved in Gardner building in Rochester. We took him all the way to the 13th floor, that 13.8. There in the substation, you take the voltage 13.8 primary, fuse disconnect high voltage into a transformer inside the substation, convert it back into two level, 48120, one substation, and 48277, the other substation. Then you can distinguish the whole system. So you don't have to worry about bonding the neutral. Utilities, though, when they come to my house and give me 7200 on that one line and the neutral, they're dealing with that neutral wire that's coming, the grounded wire. That wire is grounded at multiple locations. So anyway, they talk about it here. Grounding electrode system and conductors, we just touched on that one right in here. Enclosures, raceways grounding guys, especially at the service in this section. Equipment, when they say equipment, they mean equipment other than the service, downstream. That's in this section. And of course, bonding, can you guys see bonding goes with all of them? Bonding goes with all of them. And method of equipment grounding, that's equipment grounding, the material that you use for it. And I don't know, I've never used instrumentation meter and relays. There's a few exceptions here and a few ways and rules for the instrumentation grounding and bonding. But that's basically between the bonding, between 1, 2, 3, 4, 5, 6, 7. These are what most of us use, these 7 components in that system. Any comments, guys, about the grounding and bonding? Comments, questions? Okay, I have half an hour to cover 16 hours worth of grounding and bonding. Jeff, did you show them that 2014 code, NEC code book? You guys, that 2014 is coming? It's out. So I just want to show you one little thing about grounding and bonding before we run out of time. 220.55, 250.66, that's separated. The main bonding jumper, system bonding jumper, supply side bonding jumper, all the bonding jumper in one table, standalone table, exists right now. Grounding electrode conductor in a separate table. So I'm going to show you this one, and very quick here in our 2014, to welcome you guys to the 2014 NEC code book. So here you go. Here's 2014. Welcome to the 2014. We don't have a book yet, but we have the PDF. So there's a few changes that interesting. So let's go directly into 250. 250. Here's the 250 in 2014. It looks like exactly the stuff that we did here. That's the same picture that you guys were looking at, not a whole lot. But I'm going to take you to 250.66 here. Where are we here? 250.32.66. Okay. Did you guys recognize this table? This is your 250.66. Can you guys look at it if you have a book? It says grounding electrode conductor for alternating current. And it's only to be used for grounding electrode conductor. The same table that you do is for grounding electrode conductor, that 250.66. And it talks about if you parallel, how to size it. Now remember when we talked about 600, here's my 600 copper, it will take me to 1 aught, and larger than number 3 is optional, right? These are familiar with that one. So now this is only strictly for grounding electrode conductor. All the bonding jumper, I see somebody complain, and all the bonding jumper are going to another table. Here's another table. Welcome the 250.102C1. The newly created table. Look at all the stuff that I give you guys on that sheet. It makes it easier now. It used to be really hard. For example, can you guys see this table? It tells you grounded conductor. So you can use it for ground conductor. Remember when I said you size the ground conductor not smaller than a main bonding jumper? Now it tells you can use it for the grounded conductor, main bonding jumper, system bonding jumper, supply side bonding jumper, and for AC systems only, not DC system. So they made it really easier, the title. Hopefully, so you guys did not need to come to my grounding and bonding class if you had to wait a couple of months. We're going to be, I will be teaching that one. So this almost the same table if you look. After 2 watt, they say C notes here, and there's a couple of, this is where we start 12.5%. Can you guys see that? After 2 watt, not 3 watt for these. After 2 watt, they want you to go to 12.5%. So brand new table for you. How many of you guys do residential? Residential, do you guys do residential? Do you like the residential table that we used to have? The dwelling, the 100 amp is this size. Do you know that disappeared from NEC code book? Yeah. A 310.15 B7. Was it B7? It's gone. Yeah, now it's B7. Yeah, they moved it, but that's a different story. We'll let you guys. I almost cried when I heard about that. Almost. Okay, so that's I thought just to show you this one because it's coming in 2014, which is coming around the corner. Okay, scope of the article. This talks about, very interesting as when you go there, required, permitted, and not permitted. But the NEC require you to ground the system if you bring it to a building. If you don't bring it to a building, we don't care. Permitted is up to you, or not permitted. You cannot bond it. Circuit conductor to be grounded or grounded. If you have a delta, which conductor can you ground in a delta? Well, a delta is typically ungrounded, but if you are to ground a delta, phase B must be grounded. One phase, pick a phase, typically phase B. If it's center tap delta, meaning they went to the guts of that delta, one transform, pulled another wire, that center tap has to be grounded. If it's a Y, which conductor must be grounded in a Y? The center of a Y. So anyway, all these that we take for granted, guys, not directly from the sequence book. Location of grounding connection, when you bring the grounding connection, type and size of the grounding and bonding conductors and electrodes, method of grounding and bonding, and alternatives for grounding and bonding, like your equipment. When can you run ungrounded equipment? That's probably that equipment. You can guard, isolate. In your case, you guys did isolate or insulate, maybe use as substitute for grounding. Can I run an ungrounded? Can I have a piece of equipment and run hot and neutral to it? Yes. Here's the option: double insulated equipment, like a drill, like the equipment they use. Some drills don't have a ground. You have two prongs, not a third one on the ground, because they're double insulated. Highly unlikely that the frame will be energized and you grab it. If you isolate the system, guard the system, you put them in an area, utilities use this one, and you don't ground the frame of them because they're isolated. Only qualified people can get in there, so you don't want to ground the frame because it interferes with the operation of the equipment. That's when you isolate the system or insulate it, isolate it, or guard it with a fence. Isolate it typically with elevation. You put it in a mezzanine, 8 foot or higher. Then the code allows you, under certain circumstances, not to ground the frame of the equipment altogether. So these are very exception, guys. Here's the guarded, isolated, and insulated. I want to emphasize these are only, I would say, 2% of your situation. Maybe 5%. Account to 5% of your situation. 95% of your situation is you have equipment that's grounded. Not systems, equipment. As in the panels are grounded, the frame of this equipment is grounded, and so forth. So isolated, guarded, you cover it, shield it, fence it, or isolate it, not readily accessible. And insulated, you double insulated like tools and equipment. These are alternative for grounding the equipment. So alternative for grounding the equipment. I can think of your electronic equipment will be isolated, even though it's still grounded with its own grounding, but it's isolated from the ground though. Okay, effective ground path, guys. Here's our goal. Back to it. This is separate drive system. This is a really nice picture. If you have a ground in your separate drive system down the 208 level, the ground fault, guys, doesn't go back to the power source. It goes back to the source of it's power source, but not to the service. It has to go back to what created that current, which is a transformer. So any ground fault here, somebody asked about, was it you asked about when you have a ground fault, or when we bond it because the ground fault has to go back to this transformer. If I have a ground fault here, this will go back to this transformer. This ground fault goes back here. On this side, it's seen as circulating current, right? If you have a ground fault on this side, if you're looking at it here, you see a high current coming out of the primary and circulating between the two hots. So that's the effective ground fault current. Ground fundamentals, that's Here's my system, owned and operated by utility. They ground the reference to the ground. Here's my system, owned and operated by me. I ground my enclosures, and I tie my grounding system into the utilities through my what? Neutral. So the neutral is the bridge between your grounding electrode system and the utility that provides you the grounded and their grounding electrode system. You bridge them through the neutral. Does that make sense? You can see very clearly it's bridging them, tying them together. And also they're bridged through Mother Earth. There's another alternative path here, but that's the high impedance path that shall not be dependent on. So here's a ground fault here. 99% of the ground fault, if not more, will have a free ride over the Interstate 494 here. The other 1% or less will go to the alleys of Minneapolis. You know, because it's really high impedance here, and you might find a lot of kids working in the alleys and so forth. So you go to the high impedance. Any comments? Any questions, guys? Yes. Yes, sir.
Chad, you know, I wasn't sure if you were going to mention this earlier. It got my attention that earlier you talked a little bit about protection from lightning. I work with low voltage. I install fire alarms.
Okay.
And it's power limited. Most of the fire alarms, they have grounding conductor that goes directly to the main panel. But it caught my attention that for some applications, like when we wire to an outdoor device like a post indicator valve or fire sprinkler system, now we are required to install a surge protector, a diplex surge protector. So in that device, that module is connected to the ground. And I never really understand how that works. I just install it from instructions, so I don't know if you could explain to me how those
Surge protective device on a fire alarm system outdoor.
Right, that's right.
On an outdoor.
Yeah, it's supposed to protect the equipment, the main fire alarm panel, but I thought that was already connected to the ground of the...
Well, surge protection is a whole different story. You're protecting a surge is a surge in the voltage. So under normal operating condition, your power system is beautifully sinusoidal wave, right? So you're coming out of here, look how beautiful that thing here under normal operating condition. It's not really that beautiful, but that's that's what the wave coming to you. Now surge in the system, lightning hit the transmission line. The power coming to you. It will impose voltage into your system. A surge by definition is very high amount of voltage for a very short amount of time. That's what a surge is. Very high amount of voltage for very short, thanks God, for a very short amount of time. Otherwise, we'll burn a lot of equipment. So now we got hit by lightning. Look what happened. Now it goes all the way to the devil down here, up to the Lord, and comes back. That's my surge. And see how high the voltage is? Now at this time, your surge protective device, no ground fault, nothing. There's nothing to do with the ground. We don't have a ground fault. We don't have short circuit. We just have a surge, voltage surge because of lightning or transmission line. Your surge protector, what they do is they have a gap between them. They put them so close together. Two metallic objects, what they call yes. So they put them so close to each other that when you see this high voltage, it actually jumps the gap between them. See, it's not rocket science. Two devices very close to each other, close enough that the voltage, if it's higher than a certain limit, which we size it jumps over. So when it jumps, jumping means it chops that value here and here. It chops it down. What does it chop it down? It will be, here's my phase A, it will be taking it to, here's phase B, typically, and here's the surge protector or surge resistors, and it's sitting like this. Now when the voltage goes very high on that line, this will jump, basically ground your phase. Suck that energy into Mother Earth. In the process, it will save your fire alarm system or electronic system and so forth.
Applications use the same thing a lot of times outside.
Yeah. And every time you go outside, surge protection, we usually also required on solar photovoltaic system, the one that we did in Dunwoody, the Orlaroff, they have a surge protective device. Every time you're outdoor, because of lightning, you're required to do that. I'm not sure if they did it in 2014. It's engineering industry standard on every service panel, engineered project. We put the surge resistors right at the service.
It was a proposal in 2014 to make it mandatory for all of you guys to put, I'm not sure, I haven't checked yet if it passed or not, meaning every single service panel must have a surge protective device installed right at the panel. Right now, the engineering standard is every engineering project they will have a surge protector. But I'm not sure, I haven't checked. Does that make sense?
Yeah, but the module is, it is required to be attached to the junction box.
Yes, which is tied to the equipment grounded conductor in your case.
Right.
Absolutely, which is tied to the equipment grounded conductor. So if this is at the service, what typically it's going to be required for us, it would be to acquire the service. So it would be a piece of equipment, a piece of equipment sitting right in here, and it will tied to your phase from one side and to the ground from the other side. And if it's three-phase system, will go phase A, phase B, phase C to each one of these phases, and one to the ground. And really, if it sees a higher voltage, it just shunt this voltage to the ground and save and chop that voltage level. And there's multiple levels of them. You know, there is TVSS or surge protected device. Type 1, Type 2, Type 3. Type 1 in the line side of a disconnect, 2 on the load side of the disconnect, 3, that's the one that you plug your plasma TV in at home, the plugs that they sell. So hopefully if you have the 3 levels on an engineer project, by the time you reach the plasma TV there, each one of them will have a hit on these cuts. By the time you teach plasma TV, it'll stay there. Or your smart TV these days. I'm so excited about my smart TV. Supposed to be used as a computer. I used it to, anybody has smart TV? You guys use them? It's a computer. You can browse the internet, but we have 3 laptops. I don't see a use for it. I want to use it. I think it's a waste of time sometimes, I discovered. Okay, now this is what they use in Europe and the Middle East. So you have a grounded system, exactly the same system, a grounded system, I'm not kidding you. So the voltage, and this is not acceptable here. My voltage coming here is 220. We don't use this system. Do we use 120 only, Jeff? I've never seen 120 only as a service. Maybe in the past we used it. But typically 220, 240, 120 is the smallest voltage that we bring to a building. So here's your 220. On this side, what is it? 6.6 kV. They bring between 2 phases. So your transformer is coming out of 6.6. That's the voltage that they use. 6.6 kV phase to phase voltages. 220 here. Again, you're bringing your neutral, the utility grounding their transformer here, and you are not to ground the neutral again here. But what we do actually, you have to create a ground here though. You have to create your ground, but what you don't do is you don't bond this. So this does not exist. So then you depend on the ground fault going right through Mother Earth to clear it. Now in the US, if your system is grounded or ungrounded, you must provide another alternative to ground your equipment. So this is unacceptable means to bring a system from a power system from a grounded system or ungrounded system to your building without establishing at your building a reference to the ground through tying your equipment to Mother Earth. So they say the voltage potential difference here will be high. I dare to say, being an engineer, at that voltage, not a whole lot of high voltage. That makes a lot of, if you're doing higher than 600 volt, that becomes very high. But typically, your neutral, from your neutral to your building, you know, we talk about typical building, what, 100 feet maybe, maximum 200 feet maybe, 300 feet if it's a bigger building from this transformer to where the panel is. So at that level, the difference should not be that substantial. But based on the code, your system is grounded. You must create a grounding electrode system here and bond it to the neutral. So this talks about the shock hazard. If you guys did 17, right? It talks about if you have the shock hazard depends on the amount of current.
Yeah, two people have to leave it.
Is it at noon? Okay. Okay.
First page.
Yeah.
Before you break the line.
Okay, so we're gonna have 40 minutes here. So I'm going to pass the AB, the boarding one, the sign. And then if you are here only for the 4 hours, how many people are here for 4 hours? Only one? Okay. You're welcome to stay or leave. Please stay for lunch or leave after we break. At noon, yeah, absolutely. So I have Mr. Kojic, I have exactly 20 minutes. Okay, so let's talk about, guys, the shock hazard. The amount of current, when you have a shock, the amount of current that goes through you will depend on how will you ground it. Are you grabbing in phase A and phase B and standing right in there? That's the best perfect shock to go. And the voltage, how much voltage? Are you grabbing on 480 and 480, right? 480 voltage versus 120. So the higher the voltage, the higher the current, the easier the path right through you will decide how fast you will join the Lord. I do training, and Jeffrey do that for, what do they call themselves? There used to be North Star, Gerdau, and they do medium voltage a lot of the time. So when we talk about these one, guys, in the medium voltage system, an arc flash and arc blast is the difference between open or closed casket. It really is. Are they going to find you or not, depending on the high voltage? So I hate to be that. So when we have the PPE, the proper PPE, if you have a ground fault or a short circuit on a medium voltage, that doesn't mean you're going to survive it. But they probably will find your body though. So it's a serious business. I'm not going to go through the shock hazard. You guys have seen that one. The whole idea of grounding, guys, because we do not want you to be the easy path, the highway 494, the current will go. Now we have to be barefoot grounded here for this to work. If you are wearing rubber boots here, nothing will happen, guaranteed. I will try though. So you grab an energized object. I'm covered, man. Barefoot, outside, wet, when it just rained 4 inches, that's literally fatal. At a voltage 480, they give you 277 to ground, higher voltage pushes more current, that will be fatal. Other than that, you'll get sensation and you move on. Really, most of the shocks that we do, you get a little bit of sensation. Unless you grab on it, on an object, if you touch it, I counted like 20 times I got shocks in my 20-some years of doing that work. Most of them because I was stupid and young, doing things I shouldn't have done. A lot of them are 220. 220 to ground, So if you have an equivalent ground conductor, the equivalent ground conductor will energize the circuit before you go grab into it. You'll know about it. You'll know that this equipment is defaulted before you go touch it, because the circuit breaker will trip, and now this equipment is not working. That's the principle of operation of the equivalent ground conductor. Extended ground with the earth. Okay, so the purpose of bonding, we talked about bonding, guys. Look at the system. You have a ground fault that takes it all the way. My main bonding jumper, take this in the main bonding jumper, acts as the bridge that will bridge this energy through the neutral back to the source. That's why they want you to bond the enclosure of the service disconnect enclosure to the neutral and to the equivalent ground conductor right here. Effective ground fault path of look at this system. Can you guys tell that this system is ungrounded system? The system, when I was green, it used to bug me. I mean, there is a major difference between the system being grounded and the equipment being grounded. That's completely different things. So my system here is any of these windings of the secondary of the transformer. Are there any windings connected to Mother Earth? No, this system is ungrounded system. Do you see that the box where the transformer sitting must be grounded? You have to ground the box. That's equipment grounding. So we grounded the box. You come here, you come over here, so you have, this is if you own and operate this is if you own and operate, you pull an equipment grounded conductor here. If you want to operate, then you come over here and you create your own grounding electrode system, right here. And then you ground with your own grounding electrode system, you ground everything else. You ground everything else. You do not need to pull that conductor in an ungrounded system. That conductor here that ties this piece of equipment, unless you own and operate it. Typically, guys, an ungrounded system, I have never seen a building service that's ungrounded system. Anybody have seen ungrounded power system feeding a building? Ungrounded system typically created inside the building. For you go to the assembly line where they bring power from this side, can't be from the other side. That's an assembly line. So what they do is they have a transformer here, ungrounded, and they feed all these assembly line equipment from that transformer. So when you get the first ground fault, you're still standing. If you get a second ground fault on a second phase, you drop. So imagine an ungrounded system, the advantage of it is you eliminated interrupting your power system for 85% of your faults. Look how powerful that concept is. You have an assembly line that you remember, ground fault is 85% of your faults. Faults meaning short circuit and ground faults. 85% of your faults in your building is a ground fault. If you have an ungrounded system or impedance grounded system, you have just eliminated 85%. You come to a manager and you tell the manager that I will eliminate the ground faults, 85% of your ground faults in your building. And you continue to make canned beef or Ford or cars or so forth. Isn't that a powerful concept? So that's why the ungrounded system is very powerful. The disadvantage of it, though, that you can see is when you have transient, back to your transient, when you have a transient or you have a ground fault on it, it'll create voltage transient that burn electronic equipment. That's the disadvantage of ungrounded systems. So, but the smart analytic chat came up, since we're going to leave here, came up with a concept that's called impedance grounded. And that's kind of the hybrid between the two. So now we can take a system that ungrounded and a system that grounded and take the best of both worlds. Stability to the ground, impedance grounded will get you. Handle the transient, impedance grounded will get you. Survivability of your system means you will trip if you have a ground fault, that will get you. So that's where impedance grounded is, I believe, gaining ground on the 48277 system. Utilities use them all the time. So effective ground, guys, you have a short circuit here, will take you back into Mother Earth. Grounded system, electrical system grounding, I'm going to do, okay, so if you have a grounded system, the electrical system is grounded, the equipment, the bonding, everything is here. The only difference if your system is not grounded, what happened to the electrical system grounded? Not grounded, do you pull in neutral? No. It's the only difference between an ungrounded system and a grounded system. There is no neutral. The system is ungrounded, and because there is no neutral, there is no main bonding jumper. You don't bond the neutral. There's no nothing to bond. Go into these installation testing, short circuit. A couple of I'm jumping here because of the time. I have 12 minutes exactly. Line to line or line to ground. Short circuit is they define it as line-to-line unintentional connection or line to accidental connection, line-to-line or line-to-ground. That's a short circuit. Line to grounded conductor, grounded conductor. So if you have a phase to grounded conductor neutral, that will be a short circuit. If you have a phase to the enclosure, that's a ground fault. So all these are considered a short circuit, phase to neutral, not equivalent grounded conductor, not frame. That confuses people if you have a phase to neutral. Why do you think if you have a phase to neutral fault, it's a short circuit? Because that grounded conductor is part of your short circuit. So really, the equivalent grounded conductor does not do you any good. It doesn't interfere. If you have a short circuit between a hot and a neutral, the current will go right through the neutral. It doesn't have a free ride over the equivalent grounded conductor. The faults is ungrounded conductor of an electrical system and the non-current conductor. For example, if you have a phase to the frame, any phase to the frame, that will be a ground fault. Phase to the frame, your ground fault. Any questions about ground fault? Every time you have a hot to the ground, the frame, the boxes, that's your ground fault. Any hot to hot or hot to neutral is a short circuit. Who cares if you have a ground fault detection here? It will be looking at the current that's coming on the ground, the current that's coming back into the ground. It would not see face to face. Ground fault detection would not see face to face or face to neutral. Okay, short circuit. Let me see if impedance, so interrupting. This talks about the interrupting capability, guys, of the short circuit system. So the overconduction device have to have a capability. We'll talk about this in the second section. Capability of interrupting the largest amount of current imposed on it. Circuit impedance, short circuit, the characteristics. We'll talk about these one in the second segment. This is only chapter 1. So you guys will stay here for a long time to get into chapter 2. This is how they define a ground fault, from the point of the ground fault all the way to the electrical supply source. This is so important. So if I have a ground fault in this fixture, the ground fault path is from here all the way to the service, where the transformer bringing power is. Effective ground fault, it has to be fat enough, large enough to facilitate the operation of the overconduction device. Talk about this one. Can you guys see, here's my grounded system, ungrounded system. Look and see, it's identical. Can you guys see the difference? Identical between equipment grounding is identical. The only thing is we're not bringing one. We're not bringing a neutral here. There is no neutral, and in case the neutral, there is no bonding neutral. So look at that, very identical, the same connections. No neutral. And right here, for the equipment is bonded and so forth. So there is no neutral here, there is a neutral. That's what the difference between grounded system and grounded system. Okay, required to be grounded. This is interesting. Which one required to be grounded? Let's go directly into these guys. If you required by code to be grounded, where's the low voltage guys? If you have a control circuit and the voltage here is 150 to ground, and less than 40 volt, like 48 volt, and you're powering it from 150 to ground, you must ground the secondary here. There are exceptions. I will warn you. For class 2 and class 3 circuits, there are exceptions. So if you have a class 2 circuit, 24 volt class 2 circuits, and you're powering it from 277, you are to ground the 24 volt side of that transformer. But there are exceptions. One of the exceptions, the control circuit is controlling very important equipment here, and if a ground fault will interrupt the control circuit and create more hazard, then you don't need to ground this control circuit. Ungrounded supply this. So if you decided to take a 480 here to a control circuit, these are all control circuit, class 2 and class 3 circuit, and the voltage is 480 or 24 or 12 volt here, and you're feeding it from 480 ungrounded, you are to ground the secondary here. The secondary, not the primary. Again, there's some exception for creating more hazard. Imagine cooking nuke here, and that control circuit is controlling a nuclear reactor. And every time you have a ground fault in nuclear reactor, control circuit can create a more, or chemical, or, you know what I mean? Do you really want to ground this circuit here and take a chance that a ground fault on this control circuit will alter and interfere with the operation of a nuclear reactor or a chemical plant? So there's there's exception. But if this is feeding your doorbell, there is no nuclear reactor there, or your sprinkler system, or so. So if you're using 120 here for my sprinkler system, 120, do I need to ground the secondary? No. Only if the voltage 277. So any 120 primary, like my doorbell, 120, I don't need to ground the secondary of my doorbell. If you go outside, you go aerial, you ground. What do you think if you go aerial, like you said? You go aerial here with 24 volt, you ground it lightly. You have to ground it. So that's 50 volt or less. Most of us are 50 to 1,000 volt, right? Most of us deal with 50 to 1,000 volt. With 50 to 1,000 volt, here's your scenario. If you have, this is the most common scenario, these two guys. If you have a 3-wire system coming and you want to utilize the ground, you have to ground the center here to get you 2 voltages. If you have a three-phase 4-wire, you must ground it. If you bring a 3-phase 4-wire to a building, you must ground it. 3-phase 4-wire. If you bring a 3-phase 4-wire center tab, same thing, 4-wire center tab, you must ground it. This is 3-phase 4-wire must ground. 3-phase 4-wire from a delta must ground. Single-phase 3-wire must ground. And also single-phase 2-wire, I don't know where we use that one, where the system can be grounded so the maximum voltage to ground does not exceed 150. That's when you have to ground it to limit it to 150 or less, like 120 on the secondary here coming to feed you power, and you must ground it. So these are the ground, the system that you need to ground, and over. So now 1,000. If you're more than 1,000 guys, then you get you into grounded. So it's optional to ground. But I'm sorry, these are must ground. If you're using portable or mobile equipment, you must ground your system. You can ground it to an impedance or solidly ground it. So, but you have to ground it if it's feeding these equipments. So with your system, let me go into the ungrounded system. Okay, system permitted to be ungrounded. This is really interesting. The ones that permitted to be ungrounded. So this is where your transformer supply having primary voltage, exclusively control circuit, condition qualified person. That's where it gets you the control circuit ungrounded. Let's go back into here. These are the systems that you are allowed to bring to a building ungrounded by code. Do you see 28120? It's coming from a Y. You can't bring 28120 to a building ungrounded. 28120. You cannot. Why? It's coming from a Y. If you bring up a Y, you ground it. 240 three-phase system is permitted to come to a building, feed a building, or be a power source in a building ungrounded. So you can bring it to a system. But by the way, this could be a power system coming from the utility to your building, or a power system that you create and own and operate. So I can take my power system, put a transformer, delta, feed my single line that all of them are running at 243 phase, 480. So these are the two most important ungrounded systems in the low voltage business that we use. You go higher than that, that's now in the medium voltage. So if you're in a simple line, 99% of the time, 0.9, your simple line is running at 240 ungrounded or 480. Yes, sir.
Is there no such thing as a 208 volt power system?
There is. That would be a grounded system.
But it would be a grounded system.
Yeah, then you have to ground it.
Even though you don't use the neutral for a power system. Here you're running three-phase, you'd be running three-phase motors at 240 volts. Is there
Yes.
such a thing as a 208 system that's running 208 volt motors?
Yes.
Only.
Yes.
So you don't need a neutral on that system.
Yes. But if it's not does not qualify, if you were to feed it into a building, you have to ground it. Anybody dealt with 2.8 ungrounded? 2.8. It's coming from a Y. The reason for a 2.8 coming from Y. A 480 could be coming from a Y or a delta, right? 480 can come in from a Y or delta. 240 can come up with, 240 is coming typically from a delta, but it also can be coming from a center tap delta. But a delta like this will give you 240 or 480. So these are the three-wire system that permitted systems permitted to be ungrounded. Not required, permitted to be ungrounded. But 28120 is not permitted to be ungrounded if you're to install it in the building. Install it in the building. If your system is ungrounded, guys, I know I'm almost running out of time. I just want to mention these are the systems that you do. So you have to identify the panels at the source, which is a transformer, or at the panel itself that telling the premises that work for you guys. This is an ungrounded system. If you're looking for a neutral, you're looking for something that does not exist. So don't keep looking. Okay, circuits not permitted to be grounded. These are shall not, will not, even if you want to ground it. Number one, cranes that work over combustible fibers. If you have a cranes working here, you cannot ground the power system that drives this crane. Anybody knows why? If a ground fault will arc over a crane, what do you get? Fire. So that's fire hazard. Isolated power system in the health use. Just as open, you're sitting on the machine and they're working on you, and you're powering that equipment. That's the power that powers the equipment when your chest or mind is open is allowed, shall not be grounded. Isolated power system in healthcare facilities, hazardous inhalation, anesthesia, what location, and all these you shall not do that. That's an ungrounded system that they run it there. Electro-high-tech, I don't know, I haven't dealt with that. These also cannot be grounded. When you run an ungrounded system, you're supposed to monitor the ground. Current that goes to the ground is typically in the hospital what they use. So you're monitoring the total hazard current that's going, and it could trip or alarm. You are to monitor an ungrounded system, the ground faults, on an ungrounded system, and if it reaches a certain value, you are supposed to go, because if you allow a ground fault to sit in an ungrounded system, it will escalate into a fire. It will arc into a fire. So you're supposed to measure it. This is typically what we believe to
You're
be
measuring leak current better than?
you're measuring the current. What they do is you're measuring the current coming in and coming out, coming in and out, and if there's a substantial difference coming into phase A, phase B, phase C, and there's no neutral, and the ground, if there's substantial current coming on the ground, then you have a grounded system. Here's a couple of nice pictures. Here's a ground fault. The first phase is okay. Second phase will create a havoc for your system. Here's a good example of a simple way of detecting ground detector required by code, ground detector for our system. Could be as simple as 3 lamps with a resistor. This is voltage balancer to balance the voltage so you don't burn these. And they're tied to each phase. If one of them goes off, that's an indication that ground fault has happened into one phase. That's not that sophisticated stuff that you looked at here. That's measuring it through sensors. That's just as simple as a couple of lights. One of them dimmed or goes off. This means one phase goes to ground. Your power system will continue to properly operate. But we want you to go eliminate it because the ground fault here will create transient into your system and could escalate to a fire too. You don't want it to sit, number one. Number two, you don't want another ground fault to happen, then you have a short circuit, face to face. Here's another way, a more advanced way, where you can use a transformer to reduce the voltage here. And if you read this, all of it is an alarm circuit now, there are ground fault detection that the one that you guys said that where it can sense that you have a ground fault, sense how much current is going through the ground fault and where the ground fault is located. It can locate the ground fault for it. So you can go as low as just a lamp went off, there's a ground fault, go fix it, search for it basically in this huge plant. Or it could go as, it tells you how much current and it will sense where that ground fault is sitting on your system, which panel. So that's your grounded system. And the last thing before I let you go, guys, here's an ungrounded system. Every system, this is kind of, it tells you, even if the system is ungrounded, it's actually grounded through an inductive reactance, right? So even an ungrounded system, which is great, but even an ungrounded system is grounded through a reactance. What's a reactance? When you grab phase A, phase B, phase C, and you put them in a conduit, right? Don't you guys have, like I said, capacitor? Here's my capacitor here, here's a 480. And to the ground, this is 0. In between them is air and conduits and insulation. That's exactly what you look at the capacitor. So the utilities use this one all the time. Believe it or not, when they do transmission line analysis and they go from Becker and they bring the 600 volt, kilovolt to the Twin Cities, the impedance they take into consideration is the impedance that to go through the air, the capacitive inductance they call it. And they take this into consideration, how this will affect the voltage that sent from Becker all the way to Minneapolis. It's a big, they call it the pi. If you heard about the pi analysis, the pi, one leg of the pi is take into consideration the air between the transmission line and the ground, the air between that's the inductive capacitive reactance, which create a good problem for you in the power system. It creates a leading power factor. So what they do in substations, they go put a couple of coils, you've seen in the big substation, to actually, they have a better problem. We have a lagging power factor, they have a leading power factor. So they correct the inductive capacitive reactance by adding inductive reactance, opposite of what we do. So anyway, so everything is grounded to these systems. Okay, the last thing I want to say, guys, about disadvantages of ungrounded system, power system over voltages are not controlled. That's really probably the major disadvantage of it. Transient over voltages are not controlled. These are destructive for electronic equipment. That's why a lot of people, guys, like, we used to run ungrounded, so if you have an ungrounded system, now what they do is they go back to impedance grounded. They want the advantage of ungrounded system, which is the survivability of your system, meaning you eliminate 85% of your faults. But the disadvantage is the transient here cannot be controlled, so it will burn your electronic equipment. So the smarter than Chad decided to have somewhere in between where you have a ground fault.
So, and I'm going to stop right here. Any comments, guys? Any questions about that one? Comments, questions? Cool. Okay, so let's go break for lunch, and then we'll do the overcurrent after that one. Thank you, guys. Thank you.